IFIP General Assembly. I would like to welcome on stage Francis Beau, the SI President. A big welcome for Francis. And I hand over the deck slides to you. Sorry, let's go one forward. So, here we go.
Thank you very much.
No, just go one forward.
One forward, yes, okay.
So, Francis has a master's degree in computer science from the University of Geneva. He is a project manager in software development for finance, and he's a consultant for international organizations, multinational companies, and also private banks. He owns his own company in the field of telecommunication and ERP systems, and has been president of SI since 2020. This is his last term, which ends in 2026. So this is a big change will be happening then, because he has been leading it so well in the last 6 years. He's also interested, and this is a big part of SI, in the certification and recognition of computer science degrees, recognition of experts, and protection of IT profession, including continuous education. And before I hand over to you, I want to say that we also have a lot of people online who are watching this online. So welcome to everybody from online, from South Africa, Australia, Slovakia, Holland, and Brazil. Welcome, everybody. Come on in, have a seat. Come on in, come on in. Would we also like to invite Anthony on stage now?
Just after.
Just after. Then I hand over to you now, Francis, the president of Swiss Informatics.
Thank you very much, Nora. And ladies and gentlemen, dear colleagues, I'm very honored to open a week of IFIP workgroup meetings and annual general meeting with a symposium on IT and medicine. The location of today is adapted to our presentation, as it is a beautiful brand new building with all recent technology dedicated to the research in medicine. It acts as a hub of competences with several companies developing the technology of the future with training for medical doctor and application for the patients from the private hospital. The building has been inaugurated last year. Today, we will speak on several IT topics in link with medical field, one of the most important areas in our life. We demonstrate that our profession becomes unavoidable, and it is mandatory to have educated IT professional. Reason of existence of all high-level schools and society like SI. I'm also concerned in the medical field, as my daughter is a medical doctor in surgery. And if I am happy that IT can help medical doctor, I'm afraid of the replacement of human specialists by software and hardware. I would like to introduce Nora, our moderator of today, for the symposium. Then Dr. Nora Schlömer has done her study in renowned University ETHZ in Zurich and concluded her study with a PhD. She's a brilliant IT professional and moreover a woman in IT, and I'm really happy for that, and has worked as a project manager on important projects for several big banks in Switzerland. She's a vice president and event manager in SI. Then thank you very much, Nora, for your involvement in SI and for your help today. Thank you. Then let me now do a short presentation of SI. Then certainly you know that SI has been founded 40 years ago in 1983. We represent IT professionals. We have more or less 1,500 members, including academia, research, and business professionals. We are doing recognition of specialists in several IT domains. Then we have a title called IT Expert SI to highlight the specialists in domain of IT. We are committed to high disciplinary professionalism in IT, ethical responsibility, and continuing education. We are member of CEPIS in European level and also in IFIP, international level. Then collaboration with other national and international IT associations like Austria and Germany, which is very near from us, but also from other countries. We ensure that Switzerland remains a leading nation in engineering and in the use of digital tools. We support, we assist, and we advise the Swiss government in legal field of IT. Just to speak about some events that we have made in the past, but just to show you and explain why today we will speak about IT and medicine in these several subjects. Then we have the last 4 annual congress that we have made was in IT education, on EID, electronic identity, on artificial intelligence and cybersecurity, which will be the subject of today, but applied to the medicine and IT. We have developed a working group on EID in link with the government. And just remind you that the Swiss citizen will vote on EID in 2 weeks, the 28th of September. Then the Swiss citizen will decide yes or no, we want to use an electronic identity or not. I know that some countries already use, but in Switzerland today, it is not done. And I strongly hope that it will be done. Some other events that we have done, as an example, when we discuss about the new data protection law, which is similar to RGPD, but it's a Swiss law for protection of the data. And we also developed some courses on digital currencies, not how to invest, but how it works. And it's very complicated to understand what is a digital currency. If you one time have a look to what's a Bitcoin, then you will understand what I'm saying. And last but not least, then we have a lot of special interest groups within our society. Then just to mention software engineering, artificial intelligence, business informatics, data management, and user experience. Then please have a look to our website, then swissinformatics.org, to see what we are doing and all events that we have made and we will make in the future. Then I thank you very much. I leave the floor to Nora to continue. Thank you, Nora.
Thank you very much, Francis. Big thank you. So I welcome on stage Anthony Wong, the IFIP president. He has been president since 2022, finishing out your term this year. Thank you very much.
Thank you, Professor Nora, Vice President of SI. I actually met Nora a number of times on LinkedIn, so thank you for your hospitality.
Our pleasure.
Today. And also to President Francis for this beautiful venue and place for our General Assembly starting today. I think it's excellent. I might actually come and live here. And also welcome to all my colleagues who's arrived early for this symposium and all those online. So on behalf of IFIP, I'd like to extend our most gracious thank you to the SI for hosting us this year in beautiful Nyon. I'd just like to share a story about Nyon before I continue. 2 years ago, when I came to WSIS for the World Summit for Information Society, or for one of the meetings, the Price Hotel was astronomical in Geneva, so I decided to stay outside. And I look at the map of Switzerland, I said, what's the easiest place to get to on the train so I can get to Geneva for the meeting? And after some consternation, I picked Nyon. And it turned out to be a wonderful experience because Francis took me out for dinner as president of SI that night, and he said, I'll take you home. And he said he thought I was living in Geneva. So I said, sorry, I'm actually living in Nyon. And he said, that's excellent because I work and live in Nyon. So what a coincidence, Francis. So we're deemed to meet. So thank you again. And I think looking forward to a beautiful program on IT and medicine, and very important topic that we're all looking forward to. So thank you again, and thank you. I see a number of colleagues, technical chair, past president Leon, board members, General Assembly members. Thank you very much for coming, and those online as well.
Great. Thank you very much, Anthony. I give this to you. This is for the questions afterwards. Great, good. So now we come to the next program. So we take a look at the agenda. So we started 10 minutes late, so everything will be moved up by 10 minutes. We have Frederic talking about EID in medicine, Jan talking about AI in medicine, then we have a short break. Then after the break, we have Juan speaking about IT security. Maybe you recognize some themes that are recurring that we took up on our annual Congress, and now we are applying that to the field of medicine. And then Jacques will close the series of talks with AI and medicine as well. At the very end, there will be a show, the General Innovation Hub show, that apparently I'm moderating, so that will be a surprise for me as well. And Francis will close out the symposium at the end. So now I welcome on stage Frederik Ehrler. Please welcome Frederik on stage. So I hand this over to you, and I will introduce you. So he is an experienced healthcare information technologies professional. He is currently the research and development team leader at the University Hospital of Geneva. And he has done a PhD thesis and will speak today about EID and digital health in Switzerland, a strategic perspective. Frederik, hand over to you.
Thank you, Nora. So I'm very happy to be here to speak today about a very hot topic in Switzerland and also in the domain of healthcare in general, about the introduction of the EID in Switzerland. That's a topic which is of strong interest for the healthcare, because right now, if some of you have already deal with a security officer, you know that dealing with patient identity in healthcare is always a dangerous topic. So the idea today is to speak to you about what is the EID and how it is used, the mechanism behind, but more importantly is to speak about how it is used in healthcare. And I will give you some example of how this EID, hopefully when it will come, will impact the different solutions that are provided in healthcare. So to start, just a simple definition of an EID in 2 words is pretty simple. Until now in Switzerland, you have an ID card. It proves your identity. It gives you access to many services by validating your identity. And the EID enabled this transition into, I would say, the modern world by using digital solution to access all the services that now are accessible online. So the key features is really to confirm who you are, to perform specific action online, and to control who can use your information and when you want to use it. So really, it's like an ID when you go to the bank, when you travel. You can show a document that proves who you are, but you display when you want to. So to understand its importance in healthcare, it's interesting to see what is going on right now in Switzerland. In fact, we have a very heterogeneous environment in healthcare regarding digital identification. So with many cantonal, regional authentication factors, since Switzerland is a federal confederation, every canton has the right to develop their own solution. So I've just listed few of them, but in almost every canton you have their own identification mean that can be used to access local services provided by the state. And beside that, you have also many private companies that offers a solution for the patient, for the citizen, for the professional, and all of them, they have the solution, which many are good, but there is a real limitation to this approach, because this high number of solutions is very complicated to understand by the citizen. You have different authentication meaning that depending where you are looking for information, where you want to connect, you have to use one or another authentication. And when on your smartphone you have a whole page of authentication app that you can use, it's become really messy. Unfortunately, all these identification mean they are not completely interoperable. So it means that the information that you enter in one of them, you have to enter again in another one. So without entering into detail, that's really an obstacle to normalize and a uniform access to healthcare data and all the type of data that EID will enable. When we look at the European landscape, I would say that we are not that much in advance. Unfortunately, again, the federalism makes sometimes things a bit difficult. And in many countries, such as Estonia, which is really advanced with the e-administration, solutions like EID are deployed since many years. Austria are another example, and as well as Poland that provide a solution that is already used by more than 8 million people. So what is this Swiss EID? So the Swiss EID is this digital identity provided by the state, and it's completely managed by the state with all the guarantee that it offers with such a federal system. So it's important also to note that it's voluntary, so meaning that it won't become a compulsory system. People will still be able to use the normal ID card, but obviously there will be some more complex process. It's like nowadays when you come and you order your train tickets or your plane ticket through online platform, it's, I would say, easier than going to a desk and make all the administrative tasks. So the Confederation operates the trust infrastructure that ensures authentication, and what is interesting to understand is how all this, that EID is not just, I would say it's more than just this electronic card. It's all an infrastructure that enable the trust and enable all the different stakeholders to interact with the system. So in practice, and maybe it's not totally clear for everyone, an authentication system, it relies on three main things. You have this, what we call this e-wallet or EID wallet, which is in fact the proof, like the plastic card that you have, that can prove who you are. And with that, you will connect what we call an IDP, an identification platform that will verify that you are really who you pretend to be. And based on that, they return you some proof of identity that you can use with a service provider that will provide you some services, meaning that when you, for instance, if you ask for a driving license, you really have to prove, yeah, I'm myself, I'm allowed to drive, and not that somebody else make the request for you. So you have to verify your identity on every side. And this is done regarding this schema. You have this user that want to obtain a services, and you have these federal registries, I will show you a bit more after, that will prove on one side that the data that you provide with your electronic wallet are the one that you pretend to have. And on the other side, you have also the validation that the service provider is allowed to provide the services. So you have the trust on both sides. So this trust, as I said, it's validated on the citizen side. You, based on the information that you have on your wallet, you will control against different type of registries. The AVS is the federal identification, but also different type of registries that will control your address or any type of information that you have in your wallet. And the goal is really to ensure that your identity is valid and up to date. And on the other side, you validate that the provider of the service is the one that it pretends to be. And for this, the provider has to register themselves to these registries to prove that they're providing the service that they intend to, and that they can be trusted. So in few other words that I've said before already, but so that's the federal government that operates this trust infrastructure. It supports both public and private organizations to issue verifiable digital credential. So meaning that once you have proved that you are of trust, you can issue the identification. It has been built, obviously, with the highest standards of security. Somebody called that security by design with data production and user trust. I won't enter into detail to soft-current topic because it can be pretty complex. And it's designed to expose the minimum data to the consumer, meaning that if, for instance, you want to go to the shop and buy alcohol, you just want to prove that you above 18, but you don't want the service provider to know where you live, what's your name, and whatsoever can be stored in this digital EID. So this identity is stored into this wallet that enable the citizen to control the access and to store securely his identity. Last point, but not least, the interest is also that this framework is built to be interoperable with the European standard, the EIDAS, and that will enable, once it be deployed, to not only access to Swiss services, but also to other services in the European Union when it will be in place. Since it's not always completely clear, I've had maybe few information that are a bit redundant, but I think these concepts are pretty important. What you have to understand is that you have what we call an issuer, which is the federal state that will issue this identity that the citizen belong. This identity will be presented to the verifier, which is the service provider that will check to the registries whether the citizen is well who he pretends to be. And all these circles ensure that the trust is respected at each stage of the process. So I will focus on healthcare, but obviously the ID has a much larger potential of use. First is to confirm your identity, so you can go to the border to take a plane and so on, and show this information to be identified. It can be used in education, for instance, to prove that your diploma is well yours. You can use it for governmental services, such as taxes, requesting official documents, wedding, stuff like that, residency. It's enabled to have a single login, single sign-on, because since it's a standard and it's shared by the service provider, you can reuse the identity in a different context. Also interesting is that it will be enable qualified digital signature. Nowadays, it's still pretty complex, and it's also used in healthcare. For instance, if you have to sign medical consent, it's pretty complicated to make that in a digital way. Such kind of ID, we enable that. And again, I won't enter into detail, but for EHR, for banking, finance services, you will really, the idea is that you centralize and you make a single point of contact to access many types of services where high level of trust and security is necessary. So to obtain a Swiss ID, hopefully, if the votation goes well, it will be available from summer 2026 with an app which is provided by the Confederation. I don't know how really, not know really how to pronounce these words, SWIU, but should be that. And to access it, obviously, at one point you need to prove your identity with existing meaning a passport, an identity card, or what will be required. And as I said, this will be voluntary, meaning that if you want to step aside, it will still be possible. One point which is a bit on the side, but which still has importance because that's something that can be pretty complicated. In the hospital, we have a lot of experience of the electronic patient record, which is the national initiative to have a centralized patient file. Right now, you need to enroll yourself to get an identity, one of them that I showed you at the start. And it's a pretty complicated and long process to do on-site. Meaning that if you want to access your shared patient file in Switzerland, you first need to do an enrollment. So at one point you had to go somewhere and spend some time with a clerk that will control your data and do many different steps to get this new accreditation. So here, even though it's not yet completely clear, you should have the possibility to make on-site enrollment or online enrollment. And that would really simplify the access to such kind of EID. However, that has to be clarified because people expect that the level of trust for sensitive use case will not be sufficient with online enrollment. So it may be that on-site enrollment will be necessary for healthcare use case. So important also to understand, I showed you at the start this simple, more or less simple process of your wallet, your identity provider, and the services. And what you have to understand is that this identity provider that take your identity from the wallet, control it, and enable you to contact with a service provider. It's called AGOV, which is an initiative which is already in place in Switzerland, but it's really a key place where you have to validate your identity. So that's something which is not completely clear, at least for the one that will vote in a few days. But that's a central place where you control your identity in order to contact services. Yeah, so I won't enter into detail to this slide because it summarizes a bit what are the difference between what exists in the private or public identity provider, what is this AGOV, which is the IDP that provide you the trust token to consumer service and the federal EID, but certainly we will access to the slide. So I talked to you also about this European initiative, which is called EIDAS. So that's more or less the same initiative at the European level. It's define the standards in order to use your digital identity in the European level. And in the EID, it's intended that this EID remain compatible mean of authentication to be used at the European level. So the path to adoption. So the timeline of the EID, even though it had started certainly long before, but in 2021 we had the first votation that has been rejected for trust concern, given that the first version of the EID had to be managed by private company, so it has been rejected by the people. So following this feedback, it has been redesigned, and in September we will vote another time to make this a reality, and the release will be in 2026. So as I said, the vote will be 28th of September. The national authority recommends to vote yes to this e-identity, because it will really simplify a lot of existing process, and it will be voluntary. So right now, the survey shows that most of the Swiss population is in favor of this EID, but it remains some skepticism about some foreign people, Swiss people living abroad. So really the key point is about this trust, not just functionality, because at the end for the user, it's remain a pretty simple process, but what is really at stake is this, the guarantee of this level of trust. And we see there, it's what has been taken from the counter initiative, or the one that don't agree with this EID, is that the concern are really about the trust, the safeguard, the digital control. But I would say that's something that we live already a lot in this society, and having the state controlling this data is an interesting guarantee. So let's now deep into the healthcare domain. The healthcare domain is pretty particular regarding EID because there is right now an explosion of healthcare-related services. There is a fragmented identities, as I showed you before, and the trust, the traceability, and the security are very strong prerequisites. So we have to be careful who can access the data. That there are very sensible data. There are multiple roles, because you have patient, you have representative, you have professional that will access to the data, and you can provide temporary access because you can revert your consent of using your data or not. So that's make some specificity. So right now, it's mainly the patient and citizen that are targeted with this EID, but healthcare professional may certainly also benefit to simplify the different process to access information. So right now, it was just a small illustration of what patients experience today in the hospital. They have different systems, and on each system, they are likely to experience a different type of authentication. So the experience is pretty bad. You have to re-authentify yourself several times. There is no there is no consolidation of identity. You have to re-enter your identity on the different platform. And really, the idea with the ID is to have one source of trust that you can use across different hospitals, across different services, to access, for instance, these electronic patient reports, and to reduce the administrative cost and burden associated to this registration. So it's really the idea of moving towards a unique way, secure way of identifying yourself and access to many types of services. So what is expected tomorrow is really that at each time of the day, I won't enter into the detail, but you will use your EID, you rely on the same mean of authentication, and you can access different types of services. Just a very small link to DigiSanté, because I've heard that it can maybe of interest to some of you, but right now it's not really part of the DigiSanté initiative, but the EID is seen as a central part that will enable to provide additional services. And as promised, I will show you now a very specific use case that we encounter in our hospital, and to see how the EID will change the patient experience. So first, I speak about Concerto. Concerto is the patient portal in your hospital. It's enabled to access many types of services, appointment, medical team, medication plan, advanced directives, so many types of sensible data. It's used by more than 50,000 people a year, so it's really strongly used. But right now, we are using our own authentication flow to identify the patient, using the patient identification number to identify yourself on the platform. And that's something which is really, it seems nothing, but in fact, many of the patients, they don't know their patient ID, and it's make it very complicated. You need to have support to help them to connect to the platform. Also, what is complicated is the enrollment, because if you want to have access to some services and you're not yet a patient at the hospital, you don't have an identification number, you cannot access to the platform. So in a few words, it's like having your own identification flow brings a strong administrative dependency, flowed experience for the patient, and that's what really DID can improve as solution. So as we saw already several times before, we can log in with a unique identity. We have a high level of trust, and since everyone has one, we can use it even though you're not yet a patient at the hospital. Another example is our app for medication plan. So this app is intended to be connected to what we call the shared medication plan. The point is that the app is not intended only for the patient of the hospital, but for any Swiss citizen. And as I showed before, we have our own identification system, but which is only restricted to the hospital patient. So having identification in this app requires to put another identification system in place that complicates the stuff, that create maintenance burden and so on. And if we want to connect to the shared medication plan, we need to use another ID, meaning that the patient has to use two different ID for an app to keep it up to date. Again, here you can use a unique identity among the platform. You can match the identity in between the application and in the shared medication plan. You trust your identity is shared among the platform. Finally, last example is is an app called Infomed. Infomed is an application that oriented the patient through the most appropriate healthcare structure in an area. And the idea is to be connected with the different healthcare institutions, so you can share information about why I come, what are my administrative information to simplify the patient journey. Again, there is no universal patient ID right now, meaning that you have to re-identify in each system. It creates friction for the user. You have risk of error and duplication. And I won't repeat myself. One login for everyone. That's really the simplification. So to conclude, EID has a lot of promises, but it's not a magic wand. It won't solve all the identity issue. It should be really well implemented into the system to keep a good patient experience. It's not replacing governance, meaning that it's not because you have a single EID that it will be used everywhere. And it will not remove all the friction because, as I showed you before, some very specific use cases require higher level of security. The risk is really to continue with this fragmentation, to have this loss of public trust, because as you saw, the first votation has been refused due to the, to the lack of trust by the citizen, and that different parallel ecosystems remain in place. So the key takeaways, it's really EID is a foundational enabler for digital health. Today, everything is fragmented, and we can really narrow down to one system. We can unify the patient identity on all systems and reduce errors linked to this system. But it's not only tech that will resolve the problem, but it will depend on applying this interoperability, trust, and adoption. Okay, so to conclude, the real conclusion, not adopting this EID means that we remain into this inefficient, fragile, and siloed ecosystem, but we need to ensure the integration with real-world services, foster the collaboration between the different stakeholders, and design for reusability without forgetting the trust and for citizens and for patients. Thank you.
Yes, thank you very much. Yes, I'm also leading the EID working group at Swiss Informatics, and there we're also looking at various proof of concepts on how you use it, why you use it, in which case do you use it, and one, the physical identification of, are you really Frederick Eyre? Really? Let's see your EID. You can and how old are you? Yeah, no, I don't need to know that, but I might, as a bank or as another institution, need to know other data about it. Great, thank you. Do we have any questions from the audience? Yes, the gentleman in the middle. Oh, okay. Yep. Go ahead. Let's start at the top then. You get the microphone first. Please, go ahead.
I can start. I'm a Pole, and I'm glad that you mentioned Poland and yes. the system M-Obywatel, because it's, yeah, we are using it. Mm-hmm. Initially, I would like to say a few words more, for, except what you presented. It was developed by the biggest Polish bank, and now it's supported by the Ministry of Digitalization. Yeah. So it's state supported. Yeah. That's why it's. I think that's the key reason why it's being so well developed. Yeah. And people are using it, really, yes.
Great. That's great.
It's very popular.
Yes.
And except on top of what you said, or what you put on your slides, in that application, there are data about cars that you have, all the information about cars insurance, COVID certificates, driving license. There are much more stuff, yes. And this is yes.
Great to hear that.
Are glad about this.
Great, thank you very much.
But I wanted to say, something about the integration of medical data. It happened that I work from time to time as an IT consultant in a Polish private hospital. And then we wanted to build an integrated system for that particular hospital. They are using systems from at least 3 different providers, and it's impossible. You cannot get out data out of these systems. They are totally locked. You would need to hack these systems to get data out of them to build a new one, integrated one. And then we are talking about the second step would be to integrate medical data on a country level.
Yes.
Totally impossible.
The whole data governance topic is a huge topic. I think we won't go there today, but thank you very much for your question. Now the gentleman in the middle. Yeah?
Yeah, thanks for your presentation. My question is about change, which we know happens, and it can happen in quite extraordinary ways. When identity systems are set up, and quite rightly, they usually, of course, are set up on the basis of what exists, rather than on the basis of what will exist. And I'm thinking here about when providers, for example, change. To what extent do you think, or will a patient, for example, a user, know how long it would take for that change to happen so that there wouldn't be any inconvenience brought about? Because it seems to me that that is a part of trust. You have to trust the future as well as the present.
Yep.
So I'm interested in your thinking about this and what you're finding about this in practice.
Yeah, that's a very interesting question, because more or less we live the same situation when we have implemented the electronic patient records, where we had new way of authentication that you have to enter into the system. And like having the different system to evolve in order to be compliant with the new standards is not that simple. I would say that it will really depend on what are the incentives that are given from the state institution, what are the technology readiness and the mean of action of the different provider. We know that for the electronic patient record, there are some large institution that has integrated the authentication pretty quickly, but others are still waiting, and it's really really hard work. Yeah, of course.
Thank you.
Thank you. There's a microphone. Yes, Austria. The Austrians were here at our conference. Yes.
Actually, we have 2 systems. One is the ID, the EID, like you described it here, which is essentially government kind of, or bureaucracy kind of thing. And then we have the e-card, the e-card, which is a medical card, okay?
And they're separate.
Which is also used Austria-wide, and you identifies you to a doctor in a hospital and so on. There's one big thing that is missing, and I'm asking whether you're planning that, and you know what I'm asking, is of course, I have 3 general practitioners because I live in different places. They cannot access my data from the other physician, okay? And that happens with hospitals too. I go to 2 hospitals and I have to physically bring either a CD or whatever to the other hospital. They cannot access it. Are you going to solve that problem?
I mean, here the point of the AID is not to solve this problem, because it's really just a way of authentication. But what it will simplify is to offer a way of authentication which is shared by everyone. Meaning that today's, again, if I speak about the electronic patient records, because it's what is intended to store the data of the patient to share with the healthcare community. Right now, you have different community with different way of authentication, and if you authentify in a way somewhere, you need another way of authentication somewhere else, even though it was promised the opposite. But at least the ID will be a good step to solve this issue, but it won't solve everything.
Yes. All right. Great.
Is it just a number, or do you collect biometrics, or iris, all that data?
So all the, no, we, at least from what I know, it doesn't collect biometrics. The biometrics is used on the app of the user to unlock the authentication, but it's really, it stays on the device with private key and so on. So, but no biometric is stored on the federal level.
Yeah. All right, great. Well, Frederick, thank you very much for a very interesting presentation. We have a little something for you. Okay. Thank you. And I can take that back. Thank you very much, Frederick. All right. Now I'm very happy to welcome on the stage Jan Rutter. He is from the University of Applied Sciences of Northwestern Switzerland.
Thank you.
And he is joined the health lab under the direction of Professor Miho in this university in 2022. You have a master's in medical informatics, and your focus area is on the integration and analysis of omics data, which we will hear about. So thank you very much for coming here to present, and looking forward to your talk.
Great. Thank you very much, and thank you for the kind introduction, and thank you for having me. So what I would like to talk about, or take this opportunity to talk about a thing or a subject that we're working on in our institute for a couple of years now, which goes into the area of symbiosis, like AI in medicine, and specifically on the task like how we get from the data with the help of AI, maybe also to diagnosis. Now, from the next couple of slides that you will see, I will always, when I see, there is of course always the way of academic and industry. And now, since we are on the institute at the university, we are more strongly bound to the academic part, which is, since we're an applied university, we try to apply it to industry, but just that you have this on mind. What I would like to start with is first, when we talk about diagnosis, let's go first to the area of decision making, right? So in every field that we have, or in our daily lives, we are confronted with decisions that we have to make. And also when we go into the area of medicine, specifically like on the day of a clinician, right? They are confronted with decisions also. And some of them might be more, let's say, lighter weight, like routine decisions, which go on things or possible questions like if a clinician should, for a patient, prescribe antibiotics, wait for culture results first. Should I go for an ultrasound or straight to a CT scan with the radiation? And then there are maybe areas that are a bit more on the critical side, which go into questions like possible emergency C-sections that have to be done, or the question about how to proceed with chemotherapy, like should we start a therapy now? Should we wait until fully recovery of infection? So either way, right, in every decision or in every pace, like each decision that you make has the consequence, or has its consequence. And even if we want to go like very philosophical, even if we decide not to decide, there is some kind of a consequences out of that. But when we go again for really on the medicine part, it's an area that is very high on, it's very high on impact possibility, right? So it's a lot of responsibility. Doctors do their best, really, and the thing is just really accuracy matters in that field, because it can come also to the decision or at the point where a decision can be, in emergent cases, also the difference between life and death situations. Or when we go into diagnosis, right, we do a doctor does a diagnosis, he has symptoms, he has to decide what we do, like based on this diagnosis, we do this treatment. It also misdiagnosis, which is a thing, is brings the problems of increasing costs. Not only this, but also the affecting the trust between the patient and the doctor. So these errors can then also misguide the strategy that clinicians have and the possibility and the prognosis overall. So it's hard. It's really like doing proper diagnosis, specifically in some cases of rare diseases or more complex diseases, it's hard. So why it's so hard? I mean, on one thing, of course, every patient is different. We are humans, we are super heterogeneous. Diseases, let's say, like we know cancer or blood cancer is not equal blood cancer, multiple subtypes. And then also the thing that diseases, they have quite clear symptoms, but in other diseases, these symptoms are very vague, overlapping, so it makes it difficult. And then also now the point with the data that comes in it. So the data that is being generated, or the data that we have the capabilities also to generate more and faster. So not only going from like basic clinical records or like, let's say, like questionnaires based as clinical data that hospitals or also practices gather, but also the improvement of methods where we can just get full molecular profiles within a day for a patient, and the imaging techniques that just give us this rise and is growing fast, and also how to deal with it, of course, is getting more and more complex. So what would the goal or what we try to aim with when we say we want to see or we try to find solutions or methods how we can apply AI or help to support clinicians with it is that, as said, doctors are experts. They're really good at what they do, but also they are humans. It's a human factor. They can miss patterns. I know it's unfortunate that it's a field where it should not happen. So how can we help them? So the patterns that are really difficult to see or can be overlooked at first sight. Things like a hidden mass, a classical thing, the hidden mass on an image, which might be for a very trained eye good, being able good to spot, but let's say for maybe less experienced persons can be overlooked and can have then severe consequences. Slight changes in symptoms over time. I mean, a doctor's visit is at some point also a bit of a snapshot. The doctor sees you at this very moment. What happens during the time when you're at home or not with the doctor person being observed is another thing. Also, tiny DNA changes. I mean, our DNA, we can have so many, or everybody of us has so many mutations, kind of, in their genome, but a lot of them are not dangerous. But what is it if it's the one that is dangerous, or we don't know? So what if AI could help highlight such patterns and make them visible for the human eye? If we could achieve that, then we could maybe detect diseases earlier, and best case even before the impactful like symptoms happen or before it's very obvious. And it would support clinicians in defining the more targeted therapies, which are more tailored to each patient than for the overall population. And this could bring us closer to the concept of personalized medicine. So really tailoring the treatment to the single person, which I will get to in a few slides. And one case that I would like to give a case study on or an example on is here. We worked on a case with some collaborators on university hospitals with autoimmune diseases. So maybe the ones that maybe know a bit about the diseases, these diseases are not easy for let's say for clinicians to diagnose because, or why. So let's just say maybe on quick introduction, autoimmune diseases, our immune system is made to protect us, right? We have many cells, immune cells that help and protect us against invaders. But on autoimmune diseases, it happens that this immune system turns against the host, like our own body tissues, and can cause like chronic inflammations, can cause symptoms like skin rashes, impaired visions, and so on. And they have to be treated, these persons. But because if it stays untreated, it can go also even into organ damages. So when we see here at this point, we see also, of course, autoimmune disease is a whole group. So that means there are a lot of other like subcategories within it. So shown here, maybe the diseases, systemic lupus erythematosus, like you see in the middle, and rheumatoid arthritis. Two common diseases that are difficult to diagnose for even for specialized clinicians at some point, maybe. So why is it also? The average time of diagnosis is reported to be about 4 to 7 years. And why? Because just the symptoms are often vague. Often it's not a clear symptom that shows up, but it's things that could be either one or the other. And it just goes from, and your journey also, if you have the first symptoms, usually maybe doesn't start necessarily right at the rheumatologist or so, right? You start at your general practitioner. They try, They try a therapy. It doesn't work, you come back. And then maybe he cannot help you, she cannot help you, goes to the next doctor. And this whole play in bad cases, it can just like repeat and repeat and repeat, and until an actual diagnosis and the actual cause of your disease, such a case like an autoimmune disease, has been quietly progressing over the years, and the misdiagnosis just delayed the right treatment. So, how we wanted to try to tackle this problem, or what we wanted to try to come up with possible solutions, also like first maybe from an academic standpoint, since we are collaborating with university hospitals and we're a university institute, to see how can we bring this to a maybe at some point actionable solution for hospitals, right? So we developed, we started the development of the Personalis platform, which is a web-based solution for autoimmune diseases, a CDS, a so-called clinical decision support system, a CDSS. And it should, as said, support in diagnosis and at some point also treatment decisions for the clinician. How we do this? We did this with a collaboration with experts in the field. So we had specifically with the university hospitals of Strasbourg, Mainz, and Freiburg, also from Germany. We had the possibility to work in this very nice collaboration together to see also the point, okay, we have then this patient data, and we have not only like one data type, we have maybe multiple data types that we can use. We have clinical, laboratory, omics data, which I will get to. And we will see, okay, how can we handle this data, and also maybe come up with a method or with procedures, how we can use the data together. And then also use the mentioned AI, like the machine learning part, especially to maybe we can decipher like some complex patterns, or see are there possibilities, are there potentials that could be used maybe. And all of that, of course, since it's at the long run, try to be an actionable solution. Actually, it should be also an application that is accessible and secure, and as said, we did it in a web-based manner. So again, just with decision support to come to this point. Again, when we talk about this, that the primary goal when we talk about decision support is just that we need the primary goal of such CDSS system is to deliver the information to experts where and when it's needed, and in form that is clear, relevant, and easy to interpret. Things that might sound not so big, it's actually not that easy, especially the last parts. And where you see, you can also decide on different styles of like data decision support system ways. If it's data-driven on multiple data points collected, if it's a knowledge-based approach, or as said with machine learning models, if it's a model-driven approach. So coming back maybe quickly for the to rewind for the personalized medicine approach, or what is the problem with that, or what's the thing to mention it, why mention it? Is the problem or the thing is just that at the moment we have with medications also, or with quite a lot of medications maybe, a problem of something called imprecision medicine, meaning like that medications are made for population averages, not meaning that they are targeted specifically for the one patient that might need it. Giving an example, there might be patients, if you have like a very severe diseases, like could be breast cancer thing, or could be a schizophrenia, that there might be parts of cohorts where the medication has a beneficial effect on a certain group of patients and has the side effects. But there is also the point where you have the patients that, because of their molecular profile, they don't have a beneficial effect of the drug, but they still have the side effects. And with that, and how can you solve this? This is when you look or you try to figure out or you try to find biomarkers in this medical informatics or medical area, medicine area. And a biomarker you can think of is like a medical clue, like something like that tells you what goes on in your body. That can be either maybe from blood glucose levels, there can be CRP levels, like for how much is inflammation, or when we go even to more complex diseases like cancer for the PD-L1, like the programmed death ligand 1 a biomarker, which might be a thing, is immune checkpoint inhibitors. Would there be a possible like treatment for a cancer or not? So when we say, okay, we want to try or think of a method or like a pipeline, let's say, because we're in a bioinformatical approach here on how can we help or how can we do this or move in this direction, what data or what kind of data are we then using or what had we access to? So on one side, we had the possibility to have clinical data collected from these 3 big hospitals. So we had like questionnaires or health records about like let's say like the common, for us maybe a bit more like common kind of data. So next point, we had laboratory data. What is the difference? The clinical data goes more really into questionnaires, like so age, then also like smoker, non-smoker, body weight, body mass index, these kind of things. And then the laboratory data goes more into the direction of actual blood measurements. So mainly of looking at what are the specific cytokine concentration levels in a blood. Like cytokines are little proteins that are being secreted by immune cells, and they do a lot for the signaling within the body. So they recruit immune cells to create inflammation or regulate the inflammation. So very, very interesting and very important little proteins. So how are the concentration levels within the patients, right? And then also the so-called or the already announced omics data. So the omics data is the data that mimics or can show a person's molecular profile. Meaning, and there are several kinds of forms. They're always, or you can always recognize them in the word like omics somewhere. Genomics, proteomics, transcriptomics. And what do we had as a possibility here? There was at one point we had exome sequences, so meaning like the actual like sequence DNA or specifically the exome regions. Like so, maybe if you're a bit familiar or know that the genome has exomic regions, and these are the regions that then are actually transcribed into proteins. But just on that, so the data where we see these persons, how are on which points there are mutations, and the second omics type, the thing we had or we looked at is, okay, we look at autoimmune diseases, comes in with some kind of autoantibodies a lot of times, so that which are the ones that then cause the problems. So let's look at the actual antibodies or the actual measurement of antibodies, since again antibodies are coming from immunic cells. What happens there. And then we had also the access, or we had the possibility to look at metabolites, so meaning also small proteins that are more into the downstream procedure of patients. So let's say we have all of this data, right, some way. And the thing then with this, you heard it maybe, or you can already imagine that this data comes in various different forms, meaning that at some point, maybe patients can be represented in this data as a single row, where you see maybe on very top right the example with a little part of laboratory data, where you see some measurements of cytokine data as mentioned, like tumor necrosis factor alpha, and 2 times interleukin measurement of the blood, where you see. So nicely, every row is a patient, but below you see a very small part of the omics data region, where is which kind of mutation or which kind of nucleotide modification has this patient at this position. And now you can imagine that this one table for one patient is not just 5 rows, but it's going to be 150,000 rows or so, depending on what you look at or how much you take into consideration. And now when you think of, okay, not only the different forms, but then it's also we have different types of data, like I mean like in the formatting types, so, right? One point nicely, it's numeric things, numeric values. On the other point, the hint that we get or the data that we get is letters. So meaning like change in letter A for C. And what is then the problem also? We have to transform this somehow, because machines, as long as we want to try to use artificial intelligence or machine learning specifically on this, they can only interpret numbers. So we have to transform and code this somehow into a way that also the machine understands it or can read it. And when you think of, okay, we want to do a data model, but if we have only from the genomic field already like 150,000 possibilities that have an impact, like the so-called features that might have an impact on the decision of the algorithm, we get a huge model. So how do we do this? There are things, I mean, we are not the first ones, of course, to think about this. There are approaches that we also then applied. So we do something that is called then feature selection or feature extraction also, two type of things. Meaning that when you have maybe like all the features, everything that you have, all the changes or all the possible data points that you have, you try to select which one you take. Now, how do you do this? When it's on this large amount, and specifically since we had the benefit of doing this really in a collaborational effort with experts, we sat down with them and looked at what can we use? Is this a thing? Is this not? Because maybe sometimes a genomic alteration can look at one point very, very specific or very like interesting, but then the clinician who just has a much more experience, they say it's a very normal, highly polymorphic mutation. It's not something I would count on. So you go into this way. And then you do the machine learning on it. So how do you do this actually? So the thing is that it works mostly like this in a nutshell. You have the data. We have the data from also the diagnosed patients. So we have the benefit that we have something called labeled data. So we can use it. We can use it that we know this specific like cytokine level, this specific genomic alteration, this specific antibody count belongs to a patient who was diagnosed by the doctors with rheumatoid arthritis. This value again is for a patient that is the healthy control patient. So we can use this kind of approach, which is a supervised learning approach. So we know in our data, we know the label, or we assume the label, let's say like this, based on the diagnosis from the doctors that we have. And we feed in this patient data into the models, and we train them. We take parts of the data, we train the model, and then we try to evaluate or validate how well do different models perform. And we wanted also to see in our part not only to distinguish between is this patient or a new patient that comes in, is he likely to be an autoimmune patient or not, which might be one of the things, a so-called binary classification, yes or no. The other thing is also we wanted to see and how far or how can we look at it, and specifically in this data integration approach, how will it help if we want to go a step further and see can we also distinguish between the autoimmune diseases. And doing this, we used 3 labels, or we had the data that we could use 3 labels on it in this study here. So that we used a bunch of healthy control patients that you see on the very low left, patient samples of systemic lupus erythematosus diagnosed patients, and rheumatoid arthritis patients. So, and we used this approach. We wanted to see, let's say we use only like one data type, which is in the pilot things or the pilot projects that we know also or that we are aware of in hospitals. When you have this multiple data approach, we use one data type, which would be on the very left as an example way here to show only the clinical data. We had a nice clinical data set, nicely cured from the three hospitals. Then we see, okay, if we use like, let's say 5 different machine learning models, so all of them, why 5 different? We wanted to see if we use different kind of models. So let's see, maybe we have one that is more like on a decision tree based nature, or if we use a neural network also, or a support vector machine on it, how do they perform? Do we see also changes in the model, or is it like how does the architecture of the model also have an influence on it? And when we see on the right side, let's see, okay, we have a test only with clinical data. Let's use it and let's use our integration pipeline to see how is the results, or how are the results if we use like integrated data. So we used also then the approaches of when we had patients, or when we used for the patients the clinical, laboratory, and the genomic data. And what we saw was like a notable improvement for the prediction accuracy that we see here, that rises like from below 80% to somewhere in the area about the 95. So we see already, okay, that kind of, or like from this point of view, looks promising. So it might be something, okay, maybe we can really actually like use this data together. And also when we look at the approach, not just measuring the accuracy, so how many times was the classifiers or the algorithms actually right, let's also to see like more on the sensitivity part. So let's see the trade-off between true positives and false positives. So for this, a common thing, if you're not familiar with it, is we did rockers, meaning what you have to know, or maybe helps you to interpret it, is the more to the top left the lines go, the more accurate, or the better, or more into the perfection-wise is the classifier. The worst thing is the dashed blue line, which would be a so-called area under the curve value of 0.5, so 50%, and this would be actually be like, it would be like a coin toss. Is it like this? Yes or no? I don't know. Might be. So also there we saw from our results, and we have here, we did it on multiple models and multiple runs, and just because of the size also of the slide, we have to exemplatory things here. All of the models are shown in the paper published also. That also here we have actually a nice improvement in this direction, that we see, okay, yeah, this clinical data, or not just clinical, the integrated data might actually really give a multi-layered perspective on this, and shows maybe potential to be used. When we now talk about, okay, the performances looked better, or were better, seemed better. So then it's also, okay, but on what point, or what were the impacts by the data types also that had like the biggest decision impact for the classifier? So was it mainly like then the genomic data? Was it maybe like the metabolomic data, or was it clinical? So we wanted to see and here to show on two examples. On the very left, you have an example of one of the random forest classifiers that we did if we wanted to distinguish between the three mentioned labels. So if we have healthy controls, we have systemic lupus erythematosus patients and rheumatoid arthritis patients. And on the on the right side, you see the highest features for the distinction only between the two autoimmune disorders. And what we then saw is that we had in the top 15 features, few of them were clinical data for clinical data types. We had laboratory data. We had genomic data, so deletions or highly amount of deletions of chromosome 3. We had immunomics data, specifically again for the antibodies, so which are derived recombinate from V gene 459 and so on, and then also metabolomics data. And on this slide, maybe I have to point out on the very right side, maybe you have noticed that the most of the top features were metabolomic nature. The thing on this here was that the metabolomics data we had was for the autoimmune disease a so-called targeted metabolomics. So meaning that the ones who did the study, they had already some kind of assumption that this might be actually the metabolites or the protein that they want to look at, because they might have an effect actually. But on the other side, to say, it was nice to see that, okay, we have in all of the top 15 features, all data types were somehow in some way present. There was not just a clear overweight of one type alone when it came to the distinction of the diseases. So we have this pipeline now. We have this integrational pipeline set in an academic role. Things of making it actionable is maybe another very, very big point then. But we wanted to see, or when we started it, we wanted to think of something that maybe when we look further, how can we make it, or how can we design it and able to make it like applicable across diseases? So what we are looking at now is on how maybe can we use it on cases that are in the direction of the dengue virus, maybe. Maybe you have heard of it, maybe. Dengue virus, very in the tropical areas, 4 serotypes, meaning you get maybe infected with one serotype at vacation, conference trip, wherever. Might not be such a big issue, but if you have been infected with one serotype and then you get infected with another serotype, there is potential of a very high health risk of that. So the thing of, okay, how can we use maybe such a molecular profile or integrational approach to see, can we maybe come up with something, or is there possibility for broadly neutralizing antibodies? Tuberculosis, also a big thing, big problem still in the world. So the Mycobacterium tuberculosis is, you can be infected with the bacteria, but the bacteria is such that it can be just latent. So meaning it's just like inside your body, and maybe it stays in a latent stage always, but it's not going to be active. So, but what would be the possibility? And these people, they just have to see, or the doctors have constantly to see this patient. Is he still going to be staying in a latent stage, or is there a risk that he could get active? So also with that, could you use such an approach for prediction of a patient, possibly from a latent to an active tuberculosis stage or not? And one big thing that we are currently really looking at in our lab is on cases, and specifically on a case of plasma cell disorders. So we spoke about the type, antibodies like immunomics data. Let's see also for the field when we have plasma cells, which are in our bone marrow, and they are like, let's say, like the artillery of antibodies. The cells, they produce antibodies, they go into our bloodstream, and they are there to protect us against invaders. But there are, of course, also, unfortunately, disorders, like a known cancer type, or a quite frequent cancer type called multiple myeloma, which then creates, the cancerous cells, they create abnormal such antibodies called the M protein then, and they can cause problems and difficulties within the organs then. Another disease that you have on the right side to it is the called light chain amyloidosis, which is not a cancer type, but it's also a plasma cell disorder, which creates those antibodies, but the antibodies, they're not from a cancer cell, cancer cell, but they're toxic, and they misfold, and they create so-called amyloid fibrils, which are a bit of sticky consistency, and they accumulate then in organs. So thinking of when you have a heart muscle which has to pump nicely, it gets stuck or it gets sticky and can cause organ failure. So two different, very different types of diseases, but they have really the overlap of symptoms, and it's difficult to distinguish between them. And then also the therapy that is based, it's different which one you have to use. So that's why accurate or good diagnosis by time is crucial for the outcome or the prognosis of the patient. So maybe coming back also after showing this, or maybe giving a bit of a glimpse on what we try or hope that we can help on, is that we want to use AI as an assistant. Maybe there was some concern already also for the replacement of doctors with AI. What we try, or what we think, is that we really want to see that AI is an assistant, not a doctor. So it's still the AI supports, and I really have to stress that, supports the doctor and doesn't replace it, because the doctors are just really educated, so much experience, and they should stay in control of the decision. And AI should just be in the role to add another layer of expertise to the problem, where maybe things can get complex. This one also a very interesting or very like maybe discussed thing, and a reasonable and also a right thing to ask, the black box problem. So let's say we have a nice AI model that gives us some predictions, that give us some high features that they think, or even if they might be right, it's still like at some AI models that have good like results, we don't know where this comes from. We don't know how did they decide maybe exactly, because it's just too much to understand for us like just like that. And especially in medicine, that's problematic, right? Because we need, or doctors, we need reasoning why we should do exactly this predicted outcome or this action. And thankfully for that, this was recognized. There are also groups like and there are initiatives working on something called explainable AI. There are really good initiatives like in Copenhagen, UP2 or so that I can mention that really aim to make AI decisions more transparent and understandable so that we have, or specifically clinicians can have the reasoning to maybe take really their supported decisions they support into consideration. So summing up this maybe as a possible or future possible future for AI in medicine would be that we aim still like towards like earlier, more personalized care. So AI might really have the potential to support things like earlier diagnosis and better matching, treatment matching. But still, like as said, again, the symbiosis thing. So the doctors and AI, it has to be a thing together. So they should be seen as AI should be seen as clinical assistant, not as helping the doctors and not replacing them. And the trustworthy and more transparent AI. And going from the population-based averages, like more and more towards the individual care, which, yeah, we are not, which we are going into this direction, hopefully. With that, I just would like to thank my group, and specifically like the Professor Dr. Enkeleda Miho that I was able to work on since the last couple of years, and all of the members and alumni that did really a lot of work for this group, and also the collaborators. Thank you.
Oh, thank you very much, Jan, for making all those vast numbers and types and parameters and types of data and how they all correlate or don't correlate, and together making sense of huge amounts of data can help bring it, make it more personalized. Very good. Thank you very much.
Thank you.
Do we have any questions from the audience? Yes, in the back, in the middle. From Poland.
Yes, this is me again. In your work where you tested various ML systems, what was the quality of data, or did you get perfectly clean data, or there was some typical data like missing, outliers, and totally wrong values and duplicates?
Mm-hmm. Thank you for the question and for a lot of experience that lies behind these questions. I see the data, I have to say, as said, the data of specifically like clinical records that we got, because it was really in an organized project with the university hospital, was nice. We got multiple like data sets on the clinical side that were nicely gathered together. Also, there were some outliers, of course, that we then used. The pre-processing part is always a very, very big part in this, right? So you have to see what can we drop. Can we drop it? If it's empty, should we impute it? How do we impute it? What makes sense? Gaussian-Coppola matrices, should we do it somehow different? This is really a thing. But on the clinical side, it was really not looking bad here. But on things like when we needed, let's say, on some laboratory values or so, then we did for the studies also, we did some kind of imputation techniques, because it was on the study was based also to see, okay, we do like an approach that we can see, okay, this might be something actionable, but because it's academic, we wanted to see we generate, or we have some, we fill some gaps with synthetic data strategies, which is also described in the papers mentioned down, how we did it. And then we see, okay, we fill these gaps, and when we fill it, how does it look like? Is there the potential that it makes, there would be a beneficial outcome using this integrated data or not? But thank you for the question.
Yeah, go ahead. You have already a microphone.
Oh, okay. Thank you very much.
Yep.
So my name is Jabo Mtsweni. I'm from South Africa. My question is just simple. I wanted to understand from the scalability, point of view. Do you have some idea of the resource requirements for such work? For example, in terms of data processing and the likes.
Scalability, I mean like how much performance you actually need behind it.
Yes.
Yeah, this it's a very valid question, and thank you for asking that. As said, the actionable part, actually, I mean, this is the target, right? We do something academic to see is there potential. In the end, it would be nice to see can we actually like make it actionable in clinics. That would be the thing. There comes also a lot of things then in with software development on regulated study things and so. But only on the performance wise, I would say. What we saw is if you stay on models that are quite simple, or let's say like more like the normal ones, like decision tree things, if you have a logistic regression, classifier, support vector machine, you can handle it with, let's say, like you don't need specifically an HPC, a cluster computer. As soon as you go into more maybe complex things, which goes then maybe in the plasma cell disorder things, where you actually want to look at what are the changes in amino acid sequences that might be the patterns, then you get into much bigger vectors, and then you get into areas where you really need performance. And that would be then reliable on, you need some kind of an HPC behind it or so. So depends really on, because you need just also in this kind of things, as soon as you want a nice or let's say like fancy neural network to try, you need much more data to train it. Maybe even you can use it on pre-trained things already which are publicly available. But if you want to stay, or you can allow yourself to stay in more like normal size, minor size of data that is still like reliable kind of, and you use simple models and you just want to see what gives out these simple models already, then you don't need specifically HPC performances. Say like this maybe.
Right, thank you.
I hope that answered the question.
Right.
Thank you.
Yeah, go ahead.
Hi there. Yes, David Kreutz from Ireland. Thank you for a really fascinating presentation.
Thank you.
As a complete layman in this field, I'm intrigued by the phenomenon of hallucination and its sort of relation to the black box you were talking about, the mysteries there. And I just wondered whether this related in any sense on how you might control for the possibility of some of the true positives having been hallucinations.
Some of the true positives being hallucinated. So you mean like that some of the ones that were actual positive, like so some that were actual diseased were not captured. You mean like this story that I have to say? Okay, this is a thing. So you mean actually like the diseased ones were not seen. So the false positives, false negatives. Sorry.
Yeah. So true positives would be the
ones
model
who
saw
are
it and
and
the
have been
clinician
captured.
Confirmed.
Yes.
A false positive. The model didn't. The model saw it where it wasn't.
Yeah.
So, how many of the occasions when the model saw it and it was confirmed by the clinician were actually a hallucination by the model?
Yeah. I think I get to know what you mean. Sorry for maybe I had to just to clarify to get the question right. So the thing is really like it depends. Like always, that's why maybe I also showed or tried to show, or we show not only a slide where we see the performance of accuracy, but also then of these ROC curves, which goes more into the trade-offs to see like how sensitive it is. Because the ones specifically in cases like our diseases, right? If you want to generate or think of what is the cost that wrong labeling gets, the biggest costs are the ones in diseases, the ones who actually have it, and haven't been recognized, right? So you go more into the direction, okay, let's maybe rather like label somebody who is diseased as but he is not. But that's the thing of this of the rockers, where you try to see, because what they do actually like a computation on how is on different thresholds.
Yeah.
So that's where you try to see it.
So it's more a question of thresholds than of getting it
exactly
wrong.
Thresholds. And maybe if you saw also on the slide, there were also, we tried to see, oh god, so.
Yeah.
You maybe also see that we used also not just like one value, the averages, like the AUC values, but we also looked at the micro and macro averages. Maybe you can look at this, the difference of what is it with the classes are not exactly measured. Like let's say we don't have exactly 200 of healthy, 200 of these and 200 of these, but might there be a class imbalance? And then we would see like quite a lot of a shift maybe between these two curves in one plot. So that's how we try to see it, but it's a legit good question. Thank you.
Could you continue that maybe in the coffee break? Okay. All right.
Okay. All right.
Then we had one last quick question, and then we go for the coffee break.
Thank you again for the excellent presentation. I'm in a position to disclose what kind of tools that you used, machine learning tools or LLMs, for this exercise.
What kind of tools? You mean actually like what were the classifiers actually used or so? Or I mean like just the tools used is in Python libraries. You have the scikit-learn, libraries. You have Keras libraries. So then they're publicly accessible, so you can use it there. And we also used like specifically like in the slides here shown, because we wanted first to see like how does it work with the simpler models. Also we used pretty much a lot of the classifier algorithms from there. So it's from that libraries mainly.
Thank you.
Thank you.
Great. All right. Well, thank you very much, Jan, for your excellent presentation.
Thank you.
All right. Thank you.
Thank you.
We have a small present for you.
Oh, thank you.
All right. And now we come to our coffee break, and join us again in 10 minutes. So it's now 1:15. So at 25 after, we will start then the next set, starting with Juan, and then having also Jacques come to present the 2 afternoon presentations. See you back in 10 minutes. Let's turn on the microphone. Yes, here we are in the second part of the afternoon. I hope you had a good coffee break. I hope you guys enjoyed the views and the beautiful buildings and the delicious coffee. I really like the coffee. I heard tea was also taken. Was the tea good? The tea was good too, yes. They had really nice little baggies for the tea. Very good. So now we come to another thing which is close to my heart, which is IT security. I think we really need to protect ourselves. We need to share our data, as we saw before, with enough doctors to get a good diagnosis of what is happening. But on the other side, we have the security part, the security aspect. And this year's Congress was about IT security, as you saw in France's slide. So the next presentation is IT security in medicine, and I would like to call Juan Troncoso on the stage. Please, a big welcome for Juan. And we need also, there we go, to advance to the next one. So Juan founded Tune Insight SA, and he has done pioneer work on genomic privacy. He has 20 years of R&D experience. He's done multiple European, Spanish, and Swiss projects in health and financial data processing. So he has seen a lot of things, in particular on encryption. So he will be talking to us today about federated health data space, secure explanation and analysis from a feasibility point of view. So here I hand over to you. Thank you, Juan.
Thanks a lot. Thanks for the kind introduction. Thanks for having me. I want to talk about the conundrum or the difficulty of actually having access to data and the current need of data in order to feed AI systems and make them really intelligent, as they are meant to be, and how to be protective of the patient privacy and the data protection, basically, of the data protection regulations that impose constraints on how this data can be used and how this data can be shared. So I will bring a concept of actually using the data without having to share the data. Before I go into the topic, let me give you a brief introduction about Tune Insight. So this is a spin-off from EPFL, so the Federal Institute of Technology in Lausanne. founded in 2021, but we have been working for much longer with the Swiss university hospitals. And actually, the company was created at the request of Swiss university hospitals in order to bring all the cryptographic and data protection technology that we have developed at the lab and at the research lab in order to enable multi-site collaborations and multi-site analysis without exposing, risking, or endangering, basically, the clinical data and the medical information that is so important and so relevant in order to inform these processes and to train proper and effective ML systems. And actually, what it was also published a couple of weeks ago, Unisight has also ranked first in cybersecurity, also the top health tech medtech startup in Switzerland in 2025, so for 3 years in a row, which is quite a nice recognition in the Swiss ecosystem. So going back to the main problem and the main conundrum is that we see that there are tremendous advances in AI, ML, data science that typically in healthcare, they take a long time in order to get to benefit the patients that are the end goal, actually, to improve life, improve care, improve the quality of care, and improve the life expectancy and the quality of life of patients. And these benefits that AI, ML can bring, they take a very long time in order to reach the patients. And part of that is because there's a clash between the use of data and the sharing of this data and exposure of this data that is inherently identifiable. It's very sensitive. It takes basically all our identity, and we saw that also in the first talk about the digital identity. If we talk about health data, we go in beyond just a single identifier. And how to make it usable and impactful in this clinical research, medical research, and in the advance and application of AI. And this means that it can have an impact in patients' health, in also sovereignty, so how to avoid giving away this data that is so relevant, so important, and so identifying, and improve also and basically speed up the progress of research in its pace and its efficacy. So part of this problem is especially that we come from an idea that in order to use data, we need to get it, and we need to take it. So traditional data processing pipelines mean that if you have data that is scarce and it's also sparse into different sites, different clinical sites, but also different regions, or even different information systems from the same hospital, it's difficult. We have heard that also in one of the questions in the first talk, to get this data out of those systems in order to process it in a central place. Because this traditional idea of processing all this data together was the only way in order to make sense of this data and basically build all the links and all the relations between this data in order to progress or get some insights, get some conclusions, and improve also decision-making by using the information contained in this data. But this is not the only way. And what I will present, and I will go more into details about how this approach is composed and what are the different elements that bring the benefits and the enablers for this process, is a federated approach. So if we cannot move the data, let's let it stay where it is. So avoid transferring the data and get only the insights, the evidence, so the information that we need in order to make a decision, in order to inform this decision. We don't need to know everything about the patient in order to know that there are some confounding factors, there are some biomarkers, or there's something that is influencing the response to a treatment, the evolution of a disease, or basically the response of the patient to different conditions. So we just need the correlations, we need the evidence, we don't need the raw source data. So this is the main principle of this federated approach, where we keep the data local and we just extract the evidence, the information that is needed in order to inform these systems and make decisions. I will go more into detail about the rest of the elements that are present in this slide, but basically this alleviates the regulatory pressure because we are not transferring identifying data, personal data. So this means that from a regulatory perspective, we can go much faster because we can avoid data transfer agreements. We can avoid also, if we're talking about cross-jurisdiction or cross-country, cross-border collaboration, we can avoid extracting the data from the same regulatory region or the same country and moving it to a different country. And we can also reduce risks because we are not creating replicas of the data. And we can also enhance the freshness of the results because we're always tapping into the source data. We're not tapping into replicas that might be generated with a different periodicity or different speed. So in order to conform this platform, this approach, we have different elements. One of them is the use of privacy-enhancing technologies. So what is so-called pets, not as companion animals, but as technology that can be used in order to enhance the privacy and enhance the protection of sensitive data. And some of them include, for example, homomorphic encryption. That is cryptographic. I will not go into the technical details of all these. I will not show any formulas, just to give you the glimpse of the spectrum of technologies that can be combined together in order to arrive at the goal of using the data without sharing it. So homomorphic encryption is a cryptographic technology that enables to perform some computation on the data without having to decrypt it, meaning that we can encrypt the data, we can move it to an untrustworthy environment and get it processed there without anybody having a look or knowing what is inside of encryption. But at the same time, we can process it. So we can add, for example, different elements, we can multiply them, so we can perform some operations on the data without having to decrypt it. We have also secure multi-party computation, and these are interactive protocols where we are exchanging information that is seemingly random or completely aleatoric, and they enable the computation of a function on source data from multiple different entities without revealing the source data. So again, this is another way we have in order to extract the result of a function without sharing the source inputs of that function. And in this case, we can use this for we use this actually in the system for the keys, for the cryptographic keys that are used in order to encrypt data. And this means that we can embed also a trust distribution across the different stakeholders, because in order to decrypt any information that is encrypted with the first technique, the homomorphic encryption, we need the collaboration of everyone in order to get the result. Otherwise, the result will not be able to be decrypted, so nobody could be able to see the result. We have also federated approaches. So I've already talked about the principle of keeping the data local, the locality, avoiding the transfer of the data and transferring only the information that is needed in order to come to the right conclusion, meaning that only the aggregates, only the partial results of a computation move across sites, but the local data, the raw data, will never move out. Then we have other techniques that are, in general, following the principle of differential privacy that can bring some formal guarantees on protection, meaning that we can minimize the re-identification probability of the original records of the original patients by guaranteeing that the results of a computation follow the principles of differential privacy. And this means basically adding a controlled amount of noise on the outputs in order to guarantee that one single patient, or the impact, the influence of one single patient in the output, is minimized and it remains negligible or statistically indistinguishable. And finally, it was also mentioned in the previous talk, the use of synthetic data. Synthetic data per se is not a privacy-enhancing technology, but it can be used in order to get a glimpse on how the original data looks like, because this is typically needed in data science and machine learning pipelines. So we can create a synthetic version of the data that keeps some of the original properties of the data. Not everything can be preserved, otherwise we will also preserve the identity and all the identifying features, so we will not get any kind of privacy. And enable this exploratory analysis on the source data without having to send the source data, and knowing that we can also get formal guarantees on the protection for this synthetic sample of the data that is generated. Paired with these technologies, we also need traditional security. Means that we need to implement strong governance rules, meaning what is the right definition of the parameters of each of these different technologies, authorization policies, so we can define the process in order to authorize or reject a requested analysis on the source data, workflow restrictions, so we can enable automatic approval, for example, of some of the processes, and we'll see some examples of that, and, for example, other techniques like k-anonymity or restrict use of variables, meaning that if we have a request, for example, that will find a cohort of data of only only 2 or 3 patients, then this request will be automatically blocked by the system, and these small numbers will never be seen by the user. We also have approval, and here you can see an example, for example, of the dashboard for approval, where we can see that all the information and all the metadata corresponding to a given analysis that is requested through this federated system, and the possibility of having this privacy analysis to recommend the right parameters and discover also potential flaws or potential risks on the source data if the right parameterization is not in place. And we can go on forever. It's also audit logs, traceability, auditability, transparency, so that if there's any potential misuse on the system, it can be readily detected and corrected. So all this combined into the same platform is what we have actually put in place, and we have deployed at all Swiss university hospitals and beyond, and I will give you more details about that, conforming this federated architecture where you have an instance that is deployed close to the data, and this instance is the one that will apply all these policies, the policy enforcement, all the techniques that I mentioned before, always guaranteeing that there's no transfer of raw data outside of the clinical site, outside of the hospital, and also guaranteeing that the whole life cycle of the data, the whole process of the data end-to-end is kept protected without leakage, meaning that even this central node, that is traditional in federated approaches, will not be able to see any clear text data, because all the information that passes through this node is also encrypted. And the operation that this node does as an aggregator to take all the results coming from the different stakeholders, different clinical sites, will be done under encryption. So again, this protects end-to-end the whole life cycle of the data and enables to extract anonymous or similarly anonymous results for which the risk for the source patients can be minimized. And this has an impact also on the legal approval and ethical approval of these protocols. This is an example of a data protection impact assessment that we ran some years ago already for one of the initial deployments that we have in a couple of Swiss hospitals, where you can see the original risk of running with traditional cryptographic approaches and traditional IT security approaches in a centralized environment, so meaning moving all the data in pseudonymized form to a central place, compared to the risk minimization and the risk reduction by implementing all these different techniques at each step of the whole data process, the whole data chain. So, meaning that we can actually minimize the risks and make ethics and legal approval much faster for these kind of processes. And if we're talking about the European framework, the GDPR, and cross-border transfers, these solutions have also been proposed as technologies that can be supplementary measures to standard contractual clauses and other approaches in order to even have data collaborations between member states of the European Union, so states subject to GDPR, and other states where there's no adequacy decision. So even for those cases where there's no adequacy decision, these technologies can re-enable these kind of collaborations. So let me now go to the data lifecycle and what's the impact of having this immediate access to real-world evidence and insights generated from hospital data or health data in the research, in pharmaceutical processes, and in many different aspects that can really impact the patients by the end of the day, which is the main purpose of all this. So we normally see the data and use of data in these two different sides, let's say, where on the one hand we have all the sources of data, and also in the previous talk we saw the different modalities that are needed in order to really inform the systems and make them efficient. So it's not only clinical data, but also imaging, lab tests, wearables, omics, and all the kinds of omics data that are needed in order to get the right relations or correlations or dependencies between the data that can inform the right decision. And on the right side, we have the typical research process, but also the pharmaceutical research process that normally, we take this as an example, the pharmaceutical process, because it's a process that takes typically 10, 15 years. And most of this time is spent in waiting for data, basically, and getting the approval in order to have access to the data. Why? Because it's based on data transfer. And here we're talking about for pre-feasibility, feasibility, the NDA submission, review, etc., have all the real-world evidence that can be generated from this large hospital data pool without actually transferring this data. So this means that all these processes can be heavily and dramatically reduced. So the first thing when a researcher, a clinician, a pharma is looking for real-world data, real-world evidence, is find this data. So this findability process is already where most of these processes get stuck, because there are no global catalogs, there's no harmonization or homogeneous source of data that can be queried, and therefore most of the times we're already stuck there and we need to collect new data. And the whole data process and the usefulness also of the phased approach is that we can avoid collecting new data if we can tap into data that has already been collected and has been brought to high quality and high quality of digitization of this data. Meaning that if we're not creating replicas along the way and we are tapping always into the source data, the whole system can feed back into reusing this original data, and instead of only using it for this primary purpose that typically is provision of care, reusing this data and having secondary use of this data for research, for clinical process, for pharmaceutical processes, etc., in a secure and compliant way. Then we can go all the way down from the sandboxing, exploratory analysis, protocol definition, protocol synopsis, execution of this protocol, authorization for getting access to the data, and access to the final results. What we are changing here in this concept of fair data, so findable, accessible, interoperable, and reusable, is the concept of access, because we posit that you don't need access to the data in order to use the data. So this is what can basically reduce all this authorization process and make everything much seamless and much faster. And this together with the Data Catalog Explorer that can have this ontology, broad schema of data present across a plethora of clinical sites, can really make it much easier to find the right data and to identify the centers that can contribute to a given analysis with readily available data, thanks to this virtuous circle of reinvesting on the high-quality digital data that was already present locally. This is an example of the interface of the system that we have deployed in Switzerland, where by defining inclusion-exclusion criteria, you can search for matching patients and get not only the global patient count across the whole network, but also the breakdowns, if that's accepted or that's authorized by the policy, and also the distributions of the population for the found cohort, so that you can identify and know which centers can contribute to a given analysis and move much faster instead of having to run new data collection processes. And in terms of, because I've been talking about networks of hospitals or groups of hospitals, there are two kinds of networks. I mean, the global networks that have very broad data, but relatively shallow data. So basically, for example, all patients that go through the hospital with the typical indicators and the typical information on the EHR, the PAC system, radiology system, etc., that's collected from the patient, and disease-specific networks that are much narrower but much deeper also in the amount of data, because they depend on the specific discipline, the specific disease or therapeutic area for which the patient is treated. And this includes oncology, genomics, pharmacology, and a bit more broader value-based healthcare. So all these are cases that I could bring as example applications that have already embraced and have used successfully this federated approach. But I will focus on three examples for the next slides. So one of them is the Swiss example of this federal network that involves all Swiss university hospitals, including also Geneva, where in collaboration with the federal initiative, there is the SPHN, the Swiss Personalized Health Network, we have deployed, on the one hand, all the data preparation pipelines in order to harmonize data according to the federal standard. There is a standard based on graph model, with also mapping with all the usual standard medical terminologies like LOING, SNOMED, ICD-10, CHOP, ATC, etc. And making it possible to automatically query and immediately query all this data and discover with inclusion-exclusion criteria what data is behind and whether there's significant evidence or significant critical mass of data in order to run a subsequent analysis. And this is thanks to the fact that with all the protection mechanisms in place and all these end-to-end protection of the data and guaranteeing that we can minimize the risks for the original patients that are present in all these databases, we have this pre-approval by Swiss Ethics to run not only feasibility, but also extended feasibility, including population statistics, hypothesis testing, survival analysis, without having to go on a project-per-project basis to request approval. So this is an example on how the trust generated by this technology and the use of these federated approaches can streamline the whole process and enable, at a national level, to have this exploration of the source data from all university hospitals in this case. And of course, the governance, this is in discussion for the next steps, to have also third-party access. Another example of a more discipline-specific network at the European level is this Phase for AI consortium. This is funded by European funds in this case, and it includes multiple sites across the European geography. And in this case, it's focused on oncology. So we have specific data sets collected at the different hospitals at these different locations for lung cancer, prostate cancer, and ischemic stroke to improve the early detection of these diseases and also guide the decision-making in all these different disease areas. So this, again, is made possible thanks to this federated architecture where typically the sites will be blocked for at least 1 year, but normally 2 years or more, to export this data or centralize this data. And here they can actually train models, they can progress without having to get all these data transfer agreements and keeping the sovereignty and locality of the data they are using for these approaches. And finally, this is a case of advanced machine learning. So here we're talking about image classification for dermatology. So this is a collaboration with a university hospital in Basel and multiple sites also in Africa. Basically in dermatology, the systems are traditionally trained on white skin people, mostly because, well, here in Switzerland, for example, there are no different tonalities present in significant numbers in order to get generalizable results for these kind of models. So having access to other populations that represent other groups can make the systems the models much more generalizable, effective, and global than the ones that can be trained only on a single site. And here, again, we have this PASSION data set across 3 different sites in Africa, together with the Swiss data set. And we train basically the classifier model following this approach of federated learning plus the protection with homomorphic encryption, differential privacy that I mentioned before, so that we never disclose and we never move the source data out of the local sites, and we only move the models with confidentiality guarantees added to them. And at the same time, we can aggregate these models in order to convey the data from the whole network, but without ever disclosing this data. And if we see the results of the model that comes out of this training, we can improve actually the accuracy and the F1 score, in this case, measuring F1 score for each of the individual sites with respect to them training only on their data. So this is an example on how having more data from multiple sites can help improve generalization, improve accuracy, and improve the efficacy of these models. But we can do it without having to risk the data, and we have having to go through the long process of getting the data transferred to a central place. And if we go into artificial intelligence, then the question is, artificial intelligence is data hungry. I mean, LLMs that are probably nowadays the most popular artificial intelligence system, they need a lot of data in order to fulfill their promise and to be effective and to increase the reliability. Let's say reliability was also one of the questions in the previous talks. So here I will show 2 different cases where we can actually, thanks to federation and thanks to the application of the technologies I mentioned before, how we can improve the reliability and make a responsible use of these AI systems. And this goes on the one hand on the training of these systems, and on the other hand on the use of these systems. So how we use these systems in order to predict, classify, or actually profit from their intelligence. So the first case is the training. So if we are talking about LLMs in particular, again, as they are the most widespread and most known, the most popular at the moment, typically when we do fine-tuning or we retrain a model, it memorizes the sources, meaning that if we ask a question to an LLM, it can replicate one of the sources verbatim. And this means that if there was sensitive data used to train or fine-tune this model, there's a risk that this data will leak as a response to a given question. So here we see the impact of doing federated fine-tuning of the model and applying also memorization, minimization approaches, such as LoRa, the low-rank adaptation, paired with other privacy techniques, goldfish laws, differential privacy, etc., and how we can actually get a similar performance, and you see between the blue and the green columns, they represent the performance of the model, the accuracy of the model, when we do full training in the green without any privacy application or with any privacy technology, and with a full fine-tuning of the system, and the performance that we get in the blue column by using this federated and low-rank adaptation approach, meaning that we can recover, sorry, I swap them. So the blue is the centralized full fine-tuning, green is the federated low rank, meaning that we can recover almost the same performance, almost the same accuracy as we have for the centralized full fine-tuning without getting the same level of memorization. And this is what we are measuring here. So here from left to right, you have more memorization going to the right. So we can reduce and minimize memorization while keeping a similar accuracy in the model. Second, if we talk about the use of these systems, again, large language models have become kind of a holy grail to respond all questions right now. And when you have a general purpose system for which the end goal is not properly defined and properly scoped, then there's no way of putting limits on what the risks are into using these systems. On top of that, the LLMs are heavy and quite large if we want to go, for example, with the big models, meaning that if we have a self-hosted model, it will incur significant cost to keep running this model, both either if we buy an on-prem service or we have cloud hosting. And if we keep it remote, then we have the problem that we are actually sending the queries outside of our security perimeter. So we are sharing these prompts with a public API. That means that we can run into risk, we depend on third parties, and we're actually potentially exposing data in an unnecessary way. But sometimes if we can reduce the purpose and reduce the scope of the application, instead of going brute force with a large language model, we can employ small or light language models that are specialized, adapted, that can be put together like Lego blocks and combined together in order to solve the specific application and the specific problem that we have at hand. And in this case, we can make them much more efficient because there are several orders of magnitude smaller than the traditional, the typical large language models. They can be much more effective, efficient, they can run on a laptop, and we can actually use them for a specific purpose. And if we have a purpose definition, we can define the limits of the leakage, we can define the limits of what is acceptable for the model to disclose or to give as a result. So in the applications that we have for these small language models and this combination of different blocks for translation, harmonization, coding of the data, we apply them at the source of the data in order to help and semi-automate this translation and coding and harmonization process, but also in helping the user in getting natural language queries translated into database queries behind the curtains. So all this, again, without having to expose the prompts, without having to send the data anywhere else, because we have very efficient systems that can run on-prem and that can avoid any disclosure of the source data or the source prompt. To conclude, the impact of real-world evidence and tapping into this whole corpus of already collected high-quality data that is present at the clinical sites and reusing it for secondary purpose, for multiple purposes, is the key in order to inform not only pharmaceutical research, but in clinical research in general. And this can have a big impact in getting actionable real-world evidence that can help pharmaceutical innovation while maintaining patient privacy. It can also help in getting personalized medicine and diagnosis because it can make systems possible that can actually improve diagnostic accuracy and tailor treatments without exposing the information of the individual patients that help in order to create these systems with their data, and prepare also for this healthcare AI revolution and accelerate basically the progress of AI and the adoption of AI in medicine and in healthcare in general, while keeping also the privacy constraints and data protection and the patient rights to privacy. And in general, these federated health data spaces or these federated approaches can help both in compliance, to streamline compliance with the current and upcoming regulations. And here we're talking about the European Health Data Space, the EU Data Governance Act, the AI Act, and everything that is common that will change and force to adopt these higher level protections in order to avoid unnecessary risks on the data. Guarantee purpose enforcement, again, with this narrow purpose, narrow limitation of purpose and use, and streamline fairness, non-discrimination, as I mentioned before, for the avoiding bias, maximize data utility, freshness, depth, availability, and get security by design to enable all these processes. So here you have a list of recent publications. If you want to read a bit more on that, otherwise you can also visit our website. And well, thanks for your attention. And if you have any questions, I will be glad to answer them.
Oh, thank you very much, Juan, for that fantastic overview, expanding what we've spoken about in the first half of our conference. Do we have any questions from the audience? Yes, in the back, in the middle, from Poland. I had a group of Polish programmers. It was just amazing. So many questions.
So from my questions, you can guess that I'm interested in data engineering. And my question is about data integration in your product. You provided access to a few databases. And for me, that was a kind of mediated system. And then sooner or later, you have to integrate these data. And my question now is whether you use there is a standard fast healthcare interoperability resources. Are you relying on this standard, or you are doing, or those data sources don't follow this standard and you had to do the job by yourself?
I mean, it's always good to rely on standards if they exist and they are fit for purpose. So FHIR, I mean, HL7 FHIR is one of the most common standards for exchange of health information. The question, you have, again, to separate the primary use and secondary use of data. So normally for care and for exchanging a patient dossier or a patient information, FHIR is very good, working on a patient-by-patient basis. And in order to enable, for example, inter-hospital communication of patient dossier or patient data, or between clinics, etc., FHIR is perfect for that. Then the question is, for research, typically you work on collectives, you work on cohorts. You don't work on a patient-per-patient basis. And there, FHIR is not so appropriate, let's say. But that said, FHIR defines all the protocols, exchange protocols, communication protocols, and then you can define data models that go on top of FHIR to model the data that you need depending on the application. And there we can talk about OMOP or other different data formats. In SPHN in Switzerland, we use a specific model developed by the Swiss Personalized Health Network. There's a graph and RDF data model. You will also use SNOMED as a data model. So there are different approaches and different standards. That's maybe the part of the problem. There are too many standards and too many implementations and customizations of those standards. So even if you follow the standard, it's not completely guaranteed that you will be interoperable with everyone. And this is true for FHIR, but it's true also for OMOP and extensions or OpenEHR or any other standards for exchange of medical information. So we have connectors for all these different standards. And we can support different source systems with different data models, different schemas, and different APIs. But there's always some work in order to identify what's the pivot schema that you use in order to have the same semantics or the same meaning of what you are asking across different sites, and also to have data that is high quality and reliable on the translation between one model and the other. And for this, you always need the involvement of the local IT people at the hospitals, and there's a huge effort that has been done at the Swiss University Hospitals in order to comply with this mandate in Switzerland.
Yeah, data governance.
Exactly,
yes.
And data governance.
Yes.
So there are many factors. It's not only technology.
Yeah. All right, thank you. All right, Great. Well, another round of applause for Juan. Thank you very much. That was great. Thank you. That was a small present. There we go. I think we'll be hearing more in this area, so thank you very much. So this morning we heard about EID and medicine and the entry point and standardizing the entry point and making it unique. Then we heard about diagnostics and personalized diagnostics and how AI can help. Now we've looked at the IT security part of it, and now I would like to invite on stage Jacques Bochon, who will speak to us about reimagining health systems with AI and real-world data. So Jacques is on the board of the Swiss Medical Network and on the board of many other areas and many other companies, Chief Executive Officer of Halburn, and many other long, illustrious career. Welcome on the stage, and here is the control.
Thank you so much. Can you hear me all right? So thanks for having me. So in what's coming, yes, it's me. In fact, I will betray a secret of mine to start with. I put the presentation together, and then I just put the deck into Gemini, and I asked Gemini, give me a title for that presentation. So he came with 6 different titles, and honestly, I chose the most compelling, the most exciting. So yes, I did that. Okay, the title is quite close to what I will be talking about. So today I will be talking about how we can use data and how we can drive what we call integrated health system thanks to data, thanks to insight, thanks to actionable insight we can extract out of the data. But before everybody gets too excited with that, let me share an anecdote. So yesterday I was attending a C-level workshop about e-prescription in Switzerland. What is it? It is the ability directly from the clinical system or directly from the praxis system, as we say in Switzerland, to create a prescription, to have a seamless communication, secure communication to the point of sales of the pharmacy, and then to release the medication at the pharmacy thanks to that e-connection. And in Switzerland, every year, we produce between 30 and 40 millions of prescriptions. So what do you think is the level of utilization or adoption of e-prescription in Switzerland? If I have 30 million, how many of those are e-prescription? Any educated guess?
10 million.
What's that?
10.
Oh, that's somebody very optimistic. It's pleasant. That was a Polish optimism, was it? Okay, fantastic. Right, no, it's 300,000. 300,000, 1%. But then, you know, the whole thing comes with a QR code. So the QR code is actually the essence of the benefit, because thanks to the QR code as a point of sales, and on top of that, we heard SNOMED CT before. If we add some semantic, we can really have all the details which was in the mind of the medical doctor. So out of the 300,000, how many were then released, ausgestellt, with the QR code? What do you think? Polish optimism? 50%. 10%, 30,000. So the level of penetration and adoption of e-prescription in Switzerland is 0.1%. Okay? By telling you that, I'm explaining you that despite of some fancy example we have just seen, the IT, the automation, the adoption of digitization is at a very, very low level in healthcare in general, but because also of the fragmentation we have in Switzerland with different level of government having different accountability and responsibility, it's most probably even worse in Switzerland. Nevertheless, that was just to spoil the atmosphere right from the start. So who I am, it has been briefly presented. I spent 20 years in classical US-based IT vendors. I spent 14 years at Dell Technologies. I was a senior vice president. Then I joined a very interesting company with regard to healthcare, Innovalon, which is still one of the leaders in big data analytics for the US managed care system, Medicare, Medicaid, Affordable Care Act. We'll speak about that later on. This is what I did. And what I am today, it has been mentioned briefly, I'm the CEO of a cybersecurity company in the blockchain financial services space, which is another interesting domain, but where the adoption of IT and digitization is much higher. I am the chairman of a company called Wellgesundheit AG, which is a patient journey application in Switzerland. We belong to some of the largest institutions in healthcare Switzerland, and we have, with more than 400,000 users, we are the largest medical application in the country. And I am indeed a member of the board of Swiss Medical Network, and I am speaking in that capacity today on stage. So I am speaking as Swiss Medical Network, which gives me the opportunity to wish you a warm welcome, because the Genolier Innovation Hub is a sister company of SMN. So warm welcome on premises today. So, all right. So what I want to do today, I want first to explain you what do we mean by integrated health system, and how we want, as Swiss Medical Network, to really fundamentally change the way we deliver healthcare in Switzerland, thanks to several pilots we have put together and we have been driving very hard over the past period of time. So that's really the essence of what I want to show you. And then, based on that, I will show you how data, what I call actionable insights, can really help that transformation happen, providing the key insight around quality of care and cost, and also the risk for the cohorts or population we are taking care of. And then at the end, I will just speak from a healthcare provider standpoint, not from a science or not from pharmaceutical research. I will show you how we can make the best usage of AI, be it in process simplification, automation, but also in increasing the quality of care. So that's really what I will be speaking about. So it's not so much AI within research or I would say diagnostic, but much more about key processes linked to healthcare and links to quality and cost. So Swiss Medical Network, who are we? So we are the second largest provider in Switzerland. We have more than 20 hospitals scattered across the entire country. We have actually today more than 4,500 employees, and we also have a lot of affiliate medical doctors, more than 2,500, who work for us. So we are a relatively large entity with a lot of diversity. We set a lot of focus on having state-of-the-art equipment. This is a proof point here in this room, but also state-of-the-art research. And we collaborate quite intensively with different stakeholders of the healthcare system in Switzerland. And we have plenty of stakeholders in healthcare Switzerland, which is also part of the challenges. We are, as you can see on that map, for those of you who know Switzerland, we are covering the 4 linguistic regions, from the French part, where we are today, to Zurich and Graubünden, in the German-speaking part, Italian-speaking part. So we are very well spread. And what I have put in gray, in light gray, are our 2 initiatives, first pilots, which have now gained a status which goes beyond pilot, of integrated health system. And this is what we will be talking about. And I will take an example later on from the top left, what we call the Jura-Fuss region, and I will walk you through what we did in terms of a data pilot. So, let me explain you now, I would say, the core evil when we speak about healthcare, and why the cost of healthcare, notably in Switzerland, are continuously going up the ladder. Healthcare, the way you pay for healthcare in Switzerland. And by the way, it's in Switzerland, but in every other country almost. You have a payer. It can be a single governmental payer. It can be, like in Switzerland, 50 different health insurance or health plans, as we call it in the US, 450 in the US, whatever. The payer is rewarding the service delivered by the provider based on the fee-for-service mechanism, which is the more I do, the more I get. If I am the health system, I need to do as many operations as possible to make as much money as possible. This is the essence of almost worldwide all the healthcare processes and how payers are, again, rewarding provider. And by doing so, it's based on quantity, as you can see on that chart. And there is only an incentive to overtreat. This is the way it is today. So there is no big surprise that our prices, what we pay, premium, we pay to the health insurer in Switzerland will increase. And on September 22nd, our government will announce that those premiums will again increase by 4%. So that's current model. In the United States, that started over there, they invented another way of looking at it. And that's on the right-hand side of that chart. We call that the full capitation model. What is it? It is a value-based care agreement between a payer and a provider, where the payer will say to the provider, take care of my cohort of patients or members, and given their state, so that's their risk score, how sick are they, and given the level of quality I'm expecting from you, I will give you a fee per head. So that's a capitation model. And capitation model has been in use in several institutions and in several of those key segments of healthcare in the United States, which are what we call managed care, Medicare, Medicaid, Affordable Care Act. And you heard all the buzz around Mr. Kennedy and the way he wants to reform that, but that's another topic we'll not touch today. So the key message for you is that we need to move to a full capitation system or an integrated health system where the payer and the provider are working together and where the incentive for all the participants are fully aligned, as opposed to the current model, which is totally driven by volume and consumption of services. This is an interesting illustration in the United States. Are there American people in this room? None. But in the United States, there is a big health system called the Kaiser Permanente. It's mainly in California, but also in Colorado. And those are the attributes of that health system. So you see number of members, which are the patients they take care of, more than 12 million. In Switzerland, to compare with, we have 9 million. They have 23,000 doctors. We have 40,000 doctors, medical doctors, really. They have 300,000 employees. We have 500,000 of employees. And even worse, we have almost 10 times more hospitals than they do. Even accounting for so-called Randregionen in German, if there are Germans here, there is no way to explain such a gap, except for the fact that Kaiser Permanente has integrated the payer and the provider, and they are working under this new umbrella of capitation model. So that's a good illustration. So what do we want to do in an integrated health system? First, we want to be totally patient-centric, as you can see on that right-hand side of that slide. We want to accompany the patient from A to Z. Since we have this capitation, which is just a fixed fee, we have all the incentive to make sure that the patient or the member remain healthy, as opposed to the other system where we have all the incentive as a provider to make sure that we operate your knees as many times as possible. So that's really the idea. So we want also to have state-of-the-art acute medical treatment But then after that, we want to have a continuous engagement thanks to a lot of measures we take. We'll not go into the details to make sure that post-treatment, post-acute treatment, we have rehabilitation and we have a seamless transition. So that's what an integrated health system is all about. It's about keeping the citizen healthy and not continuously trying to provide as many services as possible. And we want to do that, obviously, around the whole span of the life of our patient and our members, as we call it, because that's a way also for us to be profitable at the end of the day. We are still a private network. We need to be profitable, and we are demonstrating it. We are moving into that direction. We just had the number of last year. In fact, whereas by the way, it is, in terms of health insurance, it is a classical basic health insurance in Switzerland that you enroll into. And whereas everybody is increasing in average 4%, we can keep our cost flat because of all the prevention we are doing with the population, with the cohorts we take care of. So to get there, we did a data pilot. And we took, you remember the Swiss map I showed you before, you had the gray zone up west, so it was northwest. And that was our first integrated health system that we started in 2023. We have 2 hospitals in that integrated health systems. We have several ambulatory centers. We have rehabilitation. We have mental health centers. So we have really the complete offering, including telehealth and so on and so forth. So that was the idea. And the idea was really to get into some level of data. But before we do that, let me tell you what were the goals we set to ourselves. So the first goal was to inject real-life data. We spoke about real-life evidence just before me. Real-life data based on unstructured data, so mainly tons of PDF. So we had plenty of symmetries of PDFs that we injected into the system. We wanted to measure the population against 2 types of KPI. The risk score, I will speak about what we call risk score in healthcare, and quality of care. I will also give you some insight about that. And based on that data analysis, based on that analytic pilot, we were able to provide tons of insight on how to set up our network and where the next direction to go to. One of the key things you can see at the bottom left of that slide is that we will go into enhancing the physician documentation thanks to AI, which is one of the directions of high importance when we look at the future. So let me now do a quick excursion. So we use US vendor to do that analysis. And I'm taking this example of Marianne, who is 66 years old. And I'm now I will explain to you briefly how does that work. How do you calculate the risk score, which is, if you want, the morbidity load of an individual based on ICD-10 coding. What is ICD-10? Those are internal coding for disease. So it is a WHO standard, World Health Organization standard. They have released 55,000 of those codes, which describe all the possible diseases. And we use a US version of that, which is 69,000, called ICD-10 CM for clinical modification coding. So you see, a lot of data is already in the cooking when we start making an integrated health system. And in fact, when we take an individual like Marianne, depending on the type of disease she has, we can assign ICD-10 coding, which then translate into those HCC, which are specifically used in the US, which are aggregation. You have around 70 of those HCC to create the risk score of such an individual. How do we do that? And we did that for the entire cohort of our pilot in Jura. So you see, we take all the ICD-10 code on the left-hand side, which describe the morbidity of Marianne. Then in the middle, we translate that into those clusters of coding, which have a specific load in terms of risk. And then we just exclude the clusters which do not increase the risk linked with Marianne, and then we come to a number. So that number is 1.2 in her case. In average, women of this age, 60 years old, they have a risk score of 0.28. So she is almost 4 times more of a risk. And you take that risk score of your cohort in a value-based healthcare, in a capitation model I was speaking about, and you go negotiate then with the payer to say, okay, my average risk score is 0.5, much higher than what you have in your stat, so you need to give me more per head in terms of capitation model. So instead of 3,000 Swiss francs or dollar a year, you give me $4,000 because out of those risks at 0.5, or in her case at 1.2 versus 0.28, as we have seen for women of her age, I have much more risk. So that was first part of our data insight. Second part of our data insight was using a quality tool. What is quality of care? Quality of care is a combination of processes, of outcome, of perception, and we have plenty of measures that we use in healthcare, like PROMs and PREMs, to measure that. But you can also measure that based on the data that we will inject into the system and making the analysis of that data. I give you an example. If you are diabetes type 1, you need to do every quarter A1C, and then you need to do every second year an eye control, and so on and so forth. And on top of that, your A1C needs to be, in Europe, below the number 7, and so on and so forth. So you have the process and you have the number. Thanks to a tool like that, we take tons of unstructured data. We'll see later what kind of unstructured data. And we are able to say for a given cohort of people with diabetes type 1, what is the quality of care which has been delivered. This is really data insight. So we used that tool as well. And then this is what we did. So we took a sample of 61,000 patients of those 2 hospitals I was speaking about, Saint-Imier and Moutier, in the north of Switzerland. We had 61,000 patients. We had 200,000 claims, so health insurance claims. We had 1.1 million of RX, so pharmacy claims. And we had more than 2,000 healthcare providers, so medical doctor, but also physiotherapist, and so on and so forth. And we used all sorts of different data, diagnosis directly from the clinical information system, for instance, radiology from the lab, and also other lab information, unstructured, flat files, or PDF. Medication, that was the claims. Utilization, we use the Swiss DRG data directly from the hospital. DRG, it's a way to cluster some procedure in an hospital to get reimbursement in the fee-for-service model. And out of all that, we use natural language processing tools, LLM, in fact, to get access to those unstructured insights thanks to the PDF. And we created a full, then, structured database with all the information individually at the individual level of those 60,000 patients. And based on that, we could, using traditional BI tools, get to those very actionable insights we wanted to access to. That was how we did it. So we could demonstrate, essentially, and that's a key learning out of that phase, that we were able to inject totally unstructured data mixed with relational database data and get to some insights. So what kind of insights? What I will show you now is just a sample of the information we could extract and some of the action we could take out of that information. So the biggest sin in a healthcare system are hospital readmission after an intervention. That's what costs the most, and that's also something that is highly preventable. So we first did an analysis to see what were the number of acute intervention in the measurement period, which was a 12-month measurement period, and how many people were actually operated, and what was the readmission rate. So you can see we had 1,500 roundabout people who were operated. Based on the risk score, remember the risk score of the people operated, I would say the forecast of the system was that 8% should be then readmitted within 30 days, and lucky them, they had only 1.7%. So, good news, because we just bought that network of hospital at Swiss Medical Network. Good news, they were doing a good job in terms of preventing readmission from people who have just been operated. But the key learning, and I'm anticipating a little bit the presentation, is that now we made the decision that thanks to AI, we can train our data, we can train our model, and we can flag in our clinical information system for the staff who are the patient leaving the hospital who needs to have a tight follow-up to prevent them from not taking their medication, for instance, and being readmitted. That was the first result. The second result, which was also very interesting, was risk management. So our AI system could identify which older adult was using medication which were risky. So for instance, for people above 65, fall risk is one of the key risks. Each time an elderly in the US fall, it costs $10,000. That's a statistic from the Medicare system in the US. So we did the same. We had 13,000 adults out of that cohort of 61,000, which were in that category. And 11 of them were combining two medications which were risky. So here, we need to speak with a provider. And you see on that chart at the bottom with the bar chart, those are the providers. And the provider with the most risky cases needs to be addressed, which is always a delicate conversation with medical doctor. That was the first one. And out of the adults we were curing for dementia, we had 65 of those. 18 of them were using a drug which can be really harmful in the case of dementia. So same case, we need to intervene and to try to prevent that. So you can see here that big data analytics has direct impact on the quality of care we were speaking about. The next one is a very famous case. Everybody understands that. So that's the risk of breast cancer in women between 46 and 62 in that case. Out of the 61,000, we had a cohort of 10,000 of those. And what they should do is every second year to have, as it's described, a mammogram being done. And we had only 3,000 which had that. So we had only 3,000 compliant females with that basic rules of healthcare. But here we come to the limit of what we were doing. Because the problem in Switzerland, unlike in the US, where when you do that, you tap into big database and have access to what I call the longitudinal patient journey, we had only access to our journey. So it's well possible that out of those 7,000 which were not compliant, many of them did that maybe in another cantons, as we call that in Switzerland, and so on and so forth. So fragmentation was an issue. But still, we could also discover that it was much more risky if you live in La Chaux-de-Fonds, for instance, and you are a female between 46 and 62. Nobody's from La Chaux-de-Fonds here? Don't think so? Okay. So the probability of occurrence of not doing the right thing in terms of compliance for breast cancer was very high. So we had the CTs here, and again, we had the provider on top. All right, so that was really very interesting because we could identify providers, identify CTs, and you can then anticipate, because prevention is the alpha and the omega that we want to achieve. And now that that next slide was for me the most interesting. And are there medical doctors in this room? No. Okay, that's what created a drama with medical doctors. That was a drama slide, okay? Let me explain you that slide. So on the x-axis, you have de-identified, we just spoke about that in the previous presentation, medical doctor, okay? On the y-axis, you have two interesting data. You have in the blue bar the length of stay, and in the orange bar the risk score. Remember the risk score we have looked at before. And what are we looking at? We are looking at heart failure, so all patients with a heart failure, and we are looking at the length of stay in hospital after a heart failure and their risk score. So what, and again, we have totally neutralized medical doctors. So what we can see, if you look at the two arrows, I can give you two interesting examples. Provider one, he has a cohort with very low risk, okay, as you can see, because they are around 0.4 for people with heart failure, but they spend a lot of time in hospital. This one is costing to the community a lot of money because he's over, I don't know what he is, but he is too much. So that's the first one. The second one, second arrow, very, very high risk score, 1.4. You remember for Marianne, she was 1.28, so 1.4, so relatively high risk score, and short length of stay in hospital as inpatient. Okay, either we can learn from best practice from him, or we need to have a conversation in terms of quality of care with this guy. So when we presented that internally the first time, we made a mistake. We forgot to neutralize the name of the practitioner. So that created the emotion I was referring to. But you understand the logic. So it's really about fostering best practice, as I put in the title, and it's really about getting the insight that can make you change the behavior of people. All right. So that was what we learned. Now, a little bit of outlook in the future, speaking about AI, but again, I just remind you, it's in this context of process optimization and in the context of provider, and certainly not in the context of research. So the first thing we want to do is to increase the quality of the documentation that our practitioners or clinicians are creating when they interact with their patient. Okay, so we are now making a pilot to use what we call a medical AI scripts. What is that? It's nothing else than based on a LLM. Can be a Gemini. We are testing Heidi Health, by the way. You can see on the top right. And it's based on Gemini. And it's really a tool that can simplify, optimize, and increase the quality of the conversation between the doctor and the patient. So first, you have a real-time transcription of your conversation, and real-time transcription in a so-called SOAP note, which is subjective, objective, assessment, and plan, which is a standard of the industry in healthcare. So he does not need to take any note, the medical doctor. That sounds stupid for many of you who are not in healthcare. But have a look. You remember what I told you, the story about the e-prescription? So this is the world we are in currently. And we are moving them from the 19th century to the 21st century in one go. Okay, so what we can also do, we can have this SOAP note summary. It is also doing the coding. Remember ICD-10 code, how important they are for the risk score and for the qualification of your cohort. That system can do the coding itself. It can integrate in the mainstream EHR, which are the health the record system we use in healthcare. And it's also compliant, very important. We heard a lot about GDPR and the compliance with multiple legislation. It's a multi-platform, and it has specialist support. What has been demonstrated by many studies on those kind of tools is that it can save up to 50% of the medical doctor time in documentation, which is one of the biggest plague for young, especially young doctors. A lot of them are just opting out because of that mess. Because of we have TARMED currently, we'll have TARDoc next year, and it will create again a wave of people quitting, I'm sure. And the GP can also save for each encounter 10 minutes, but more importantly, and that's a key message, he keeps eye contact with the patient. And that's where you discover plenty of things. Freud was used to say that quality of this dialogue between the medical doctor and the patient that leads first to immediate improvement of the health condition in many instances, as opposed to have a doctor just typing on his PC while you are trying to explain you what is the issue, and a very accurate documentation. So we are rolling that out, not only for our own medical doctors, but to the associate medical doctors. So we expect to really increase the effectiveness of our health system. And another thing we are doing at Swiss Medical Network, we are working on this big project, which is an Inno-Swiss project, which is our agency for innovation in Switzerland. We are working with several university hospitals that you can see on the right-hand side of that slide. And it's about precision oncology. It's about a patient journey in the case of precision oncology, leveraging at multi-stages or multi-steps of the patient journey, precisely, both the data we can provide and the AI agent we can use. So we are using, in that case, AI agent for the diagnostic. It's obvious, but we are also using several AI agents for what we call the tumor board, which is a key process in healthcare for people suffering from cancer, because it's a cross-functional, multidisciplinary process that needs to be properly documented before, properly documented after, and have follow-up. And AI agents are really gold to do that. And they will be developing also an application that will be combined with an assistant that will be an AI assistant. So you can see that even for such a journey, for people with cancer, we can have immediate impact of using the quality we can extract from those AI systems. And we, Swiss Medical Network, we are more in the integration of regional hospitals, the sub-project 7, as we call it, and we will be providing data with all my comments about the data. All right, almost on time. That was it. And maybe a last comment from my side. We deeply believe, and I deeply believe that AI is not really the future of medicine, but medical doctor using AI will really make the difference at the end of the journey. Thanks for your attention.
Well, thank you very much for that amazing overview of how you want to use AI and how it should be turned. It's similar to the conclusion we came to in our Congress 2 years ago on AI. Similarly, not doctors, but the population in general. It's not AI that is the future. It's how people in general use AI and apply AI. So I have a bit of a nasty question for you.
Oh,
I would like to apply your risk assessment thing to Kaiser Permanente and the Swiss population. What is the health score of people doing Kaiser Permanente with very few doctors compared to the health score of Swiss population with lots of good doctors?
That's a good point. So we are, in Switzerland, we are swimming in luxury.
Yeah.
Okay.
So we are super healthy.
We are
super high
we are healthy because we are super wealthy. So wealthy equal healthy. So which is a fair statement to make.
Yeah.
But we are reaching the limit of that system. So number of people who are falling off the board because of those continuous increase in healthcare costs is soon getting not sustainable.
Yeah.
okay? And what will be the reaction? So the people, because it's a long story. Healthcare is extremely complex. It's an ecosystem. You get crazy when you get into it. I just started 5 years ago. I am still spinning when I think about that complexity. But the reaction will be things like, okay, we have multiple payers. They cost too much because they have too much what they call in the US medical loss ratio, which is what a health insurer spends on non-reimbursement for the patient. And they may say, okay, let's kill all those insurers and have only one payer. Okay, stupid reaction. We know one-payer systems. France, French people, sorry about that. UK, NHS, sorry about that. So we know what it means, one-payer system. It's not good. So we have this pressure. So the cost pressure has increased significantly. And yes, the quality is good, but not as good as we can think. So my chart where you see the different lengths of stay, depending and compare with the risk score, tell me that we have plenty of opportunities. And to your point, that's right. We have this readmission, hospital readmission. What was that? Only 1.7%, whereas 8 would have been the norm given the risk score. So we are better, but still, they could have saved 250,000 francs a year by not doing so. So we have plenty of things we can do.
There are so many factors that come into play in these things.
And it's time to optimize. And what I was explaining about the poor level of automation, so of IT processes, digitization, that's terrible. And it will bite our nail at some point.
No, fully agree. Great, thank you. Any other questions? The Polish guy in the back.
Yeah, hopefully an optimistic question.
Yes, I wanted to increase the level of optimism in this hall, saying that in Poland, digital the prescriptions are only possible thing that work now. I haven't seen paper prescription for years. What I get a prescription number as a text message and the full prescription PDF by email. When I'm sitting...
with a QR code?
No, but you have a number. You have a number that you go to a pharmacy. What is your prescription number? 1, 2, 3, 4. Ah, okay. And you can go to any pharmacy in Poland and you get this medication.
So it's way better than in Switzerland. But there is a small but, if I may.
Yes.
The small but is that without a QR code, you cannot prevent a lot of things to happen. You need the QR code to prevent fraud, for instance, multiple utilization of the same prescription, and so on and so forth. So you need to have a grand ledger keeping track of all that.
No, it's...
Unless the Polish are smarter.
To buy a medicine, you have to provide your national ID. And they check it. There is a central nationwide register. So you cannot buy more. You cannot give this prescription to anybody else. It's secure. And it works perfectly. So come to Poland. Come to Poland. That's the conclusion.
No.
Get treated in Poland.
What is their health score?
So I just have a question.
Sorry? Yeah.
Okay, in Austria we have the e-card. Okay.
Yes, you have the e-card.
Essentially, what is happening is the doctor puts a description on your e-card. You go to the pharmacy and show your e-card, and then you get your prescription.
Not even a PDF, then.
So
even more.
In that way, also there are no paper descriptions. There is no QR
That's
code
way better.
or anything. Okay. The only problem is the e-card, as it turns out, does not really identify. There is no picture on it or something. So you can loan your e-card.
We are back to fraud, abuse, and waste. Absolutely.
And currently they are changing the system, and they will have an identification on the e-card, like on a passport or something.
Yeah, but it's already way better. And by the way, everybody in Switzerland has a health insurance card. So applying such a system would be easy. But then we have our federated system, which is a big business preventer.
Austria, of course, has federated things too, but because we have different health insurance organizations. So it took a long time to establish it. The problem is it's only for this very limited use. Okay, it could have been used for many more information.
It's a good start. If we have 40 million of prescription, you must be in the same ballpark.
Yeah. Oh, you could also put biometric data on the health card.
Absolutely. Yeah. Yeah, that's why. That's why. The gentleman over there.
Yes. Yes. No, thank you very much for the presentation. I've listened to all of them. One thing that is just lingering in my mind, particularly on your conclusion, doctors using AI will sort of be the key, is how much effort within your network are you putting in bringing the doctors up to speed? Because just like, let's say, for example, in the education sector, if students use AI but they are not well trained in terms of how to even use it ethically, it can then lead to even more, dire consequences. So I just want to understand from your perspective, what are we doing to also bring the doctors on board?
That's a very good question. So too little, obviously. We have, in terms of action we have taken, we have just started. So this year I was just standing here and was making the opening keynote in front of all our management, 500 people, 400 people sitting around here. And it was an education about the essential foundation of AI. Because what I can claim is that if people don't know exactly what it is, you have no idea. How many people believe that, for instance, an artificial neuron is a chipset from NVIDIA? You would be surprised. You would be utterly surprised. In the lay community, how many people believe something like that? And when you tell them it's 20 lines of Python code, that's mind-blowing to them. Okay? So it's incredible. And when they understand that, maybe they adopt, Because before that, fear was a dominating factor. So we do those education. We also have now put in place a portal where through APIs, we have multiple LLM they can have access to in a secured environment, which is our environment. But it's only the beginning.
I have just one question for you. When I'm Swiss citizen, and thank you very much for your approach and your presentation. I like very much that you have a focus on the health of the citizen and not on the cost. Not talking about the cost, but now what's next? When you do a survey, you do a lot of presentation, etc., etc. But what's next? In concrete way with the government? Then do you propose something? Do you propose to change insurance costs? What's next in your idea?
So what we very concretely do, Swiss Medical Network, we expand this model. So we have a first integrated health system in the Jura-Fuss. Okay, this one we have now several thousand members. Okay, and that's really the model I described, capitation. And that will reduce the cost. We have already proven that because we don't need to increase the health plan cost, okay? And it will also, we are also deeply convinced about that, increase the health of that population. This year, we have started a new integrated health system in Tessin, the Italian part of Switzerland. In 2026, we will open a new one around Zofingen in the center of Switzerland. And the year after, we have 2 additional networks we are looking at. And we, SMN, we are buying the hospital. Zofingen, we bought that from Kantonsspital Baden, Aargau, excuse me. And we continue to do that. So we are sick talking. It's pointless to talk to our bureaucrats and to our politicians. It's too an emotional topic. People, when you try to explain something, imagine the level of knowledge you need to have to be able to explain why. And I am in front of a very educated audience. So we are sick talking, and that's why we are doing now. We are just doing. And it raises a certain level of interest because we see we work with Visana, which is a health plan in Switzerland, one of the large ones. but we see other health plans starting and following the lead. So I think we are leading by example.
Wow.
Thank you.
Excellent. Well, let's...
No. No, in fact, you remember the capitation model I was talking about? So Visana is a health plan, that's a payer, and we are the provider, healthcare provider. So the agreement we have with them is that in the first 3 years, we share the pain and the gain. So we do full capitation, but if we are completely off with our cost, they cover 2/3 of our cost. And now this year we had gain. We were profitable despite of having the lowest health insurance fees, and we gave them some money back. And in 2 years from now, it will be totally full capitation. It's for profit because we believe that model can make money through all the measures I have described, but we start with this ramp up.
Great, thank you very much. Here's
Thank
a small appreciation token.
Thank you very much.
Excellent speech, very good.
Thank you very much.
And thank you very much for hosting us in your beautiful presence.
Much welcome, you all.
Yes, really appreciate that. So now we will see a little bit more also about these premises, because now we will have, just a sec, where are my notes? Oh, I lost my sheet. So now we will have an overview of Genolier and the show. So do I need to press any buttons, or will this happen magically? There we go.
Then I would like to say some words to conclude the day, the symposium. Then with the wonderful view we have today, then we have a chance a little bit, but sunshine is missing. But I would like to thank you, all the speakers, for their presentation, then high-level presentation. I really appreciate every presentation of today, really interesting. And I would like also to thank the General Innovation Hub for the opportunity to use the installation, and I would like also to thank you all participants of today. Then we have a lot of participants online, then on YouTube, but they have seen all the presentation. And I would like to say that SI is committed to enhance IT for the future, and I hope that today you have enjoyed all these high-level presentation. Then I close now the symposium and welcome for the cocktail, and will be done in the entrance of the building. Then thank you very much.